Hello there and welcome to Life Beyond Seen, a quiet place where curiosity slows its breathing and science takes a softer voice. Wherever you are right now, whether the room is dark or lit by a single lamp, whether the day is just ending or hasn't quite begun yet, I'm glad you're here. Tonight, we're turning our attention to a place that looks simple on a map, but resists understanding in ways that still surprise the people who study it for a living. A place that appears empty, flat, and frozen, yet remains one of the most carefully avoided regions on Earth. Not because it is forbidden, not because it is hidden behind fences or warnings, but because even now, with satellites circling overhead and machines built to survive space, there are parts of this continent that scientists choose not to enter. We're talking about Antarctica, a landmass so vast that it could swallow entire countries without looking crowded, and so quiet that sound itself seems to hesitate before crossing it. From afar, Antarctica feels settled. It has been photographed, mapped, crossed by aircraft, measured by radar, and studied for generations. And yet, when you look closer, when you stop thinking of it as a white shape at the bottom of a globe and start thinking of it as a physical place with weight and motion and consequence, something shifts. There are areas there that remain deliberately untouched, not skipped out of fear exactly, but out of respect for what the environment does to both people and machines when conditions align just slightly the wrong way. Before we go any further, take a moment to notice where you are. What time is it for you right now? Is it late enough that the day has started to blur, or early enough that the world feels suspended between intentions? Antarctica exists in a permanent version of that feeling. Months of darkness, months of daylight, no gentle transitions, just long stretches of extremes that don't care whether humans are comfortable with them or not. If you find this kind of slow exploration calming, or if it helps the mind loosen its grip on the day, a like or a quiet subscription helps this space reach others who might need the same pause. And now, without rushing, let's ease into the story itself. When people imagine Antarctica, they often picture a blank canvas, a white surface with nothing to interrupt it. No cities, no roads, no visible life. That impression isn't wrong, but it is incomplete in a way that matters. Antarctica isn't empty in the way a room without furniture is empty. It's empty in the way the deep ocean is empty, full of forces that don't announce themselves until you're already inside them. One of the first misunderstandings about Antarctica is the idea that scientists simply haven't gotten around to exploring all of it yet, as if the unvisited areas are waiting patiently, like unchecked boxes on a to-do list. The reality is quieter and more complicated. Many of the places scientists avoid have been seen, measured indirectly, and analysed through layers of data. They are not unknown in the sense of being invisible. They are avoided because what lies there makes meaningful work nearly impossible, and sometimes actively dangerous, even by polar research standards. Antarctica does not behave like land elsewhere on Earth. The ice is not a surface resting on solid ground. In many regions, it is kilometres thick, flowing slowly but constantly, reshaping itself under its own weight. What looks still is often moving. What looks solid may be under tension, and what looks safe today may fracture without warning tomorrow. There are areas where the ice sheet moves faster than expected, not like a river, but like a frozen conveyor belt. Scientists know these zones exist because satellites can track subtle shifts over time. But being able to observe movement from orbit is very different from standing on it. Instruments placed in these regions have a habit of vanishing. Not dramatically. They don't explode or sink in a cinematic way. They simply drift, tilt, disappear into cracks that were not there when the equipment was installed. Even the act of travelling across Antarctica is more complex than most people realise. There are no fixed roads. Routes are re-established constantly based on ice conditions, crevasse mapping and weather models that are updated almost continuously. In certain areas, especially far from established research stations, the margin for error narrows until it effectively disappears. One miscalculation in snow load, one unexpected temperature shift, and the ground beneath a vehicle can give way into a hidden void tens of meters deep. These crevasses are not rare anomalies. They are part of how Antarctica breathes. Some are visible, sharp lines splitting the surface. Others are bridged by thin layers of snow that look no different from solid ground. Radar can detect some of them, but not all. And radar data is not always reliable in regions where ice density changes unpredictably, or where layers have folded over themselves through centuries of pressure. So why not send robots instead? That question comes up often, and it seems reasonable. Machines don't feel cold, they don't panic, they don't need sleep. But Antarctica has a way of defeating technology not through violence, but through persistence. Extreme cold affects batteries, wiring, lubricants, and sensors. Materials that function perfectly in space can fail on the Antarctic plateau because the temperature difference between sunlight and shadow is too abrupt, or because fine ice crystals infiltrate seals that were never designed to keep out something so small and abrasive. There are places where autonomous vehicles lose orientation because the magnetic field behaves unpredictably. Areas where GPS signals degrade or become unreliable due to atmospheric conditions. Zones where communication with satellites drops out for hours at a time, not because of equipment failure, but because the geometry of orbit and latitude creates blind spots that cannot be easily corrected. When a machine stops responding in Antarctica, it cannot be easily retrieved. Sending a recovery team may cost more resources and introduce more risk than the original mission justified. As a result, some regions have developed a reputation within the scientific community, not as mysteries to be solved, but as locations where the cost of curiosity currently outweighs the benefit of the data collected. Weather plays its own role in this quiet avoidance. Antarctic storms do not behave like storms elsewhere. They can form with a little warning and linger far longer than predicted. Winds accelerate over ice sheets, funneled by subtle changes in elevation that are invisible at ground level. Temperatures can drop tens of degrees in a matter of hours. Visibility can vanish completely, leaving even experienced polar guides unable to distinguish ground from sky. In some regions, weather models are less reliable because there are so few ground-based sensors to feed them data. This creates a feedback loop. The lack of stations makes predictions less accurate, and the inaccuracy makes placing stations riskier. Scientists know these gaps exist. They talk about them openly. But acknowledging a blind spot is not the same as rushing into it. There is also the human body to consider. Even with modern gear, the cold imposes limits that cannot be negotiated. Prolonged exposure affects cognition. Decision-making slows. Small mistakes become more likely. And in an environment where rescue can take days or weeks, the margin for those mistakes is thin enough to disappear entirely. This is not about fear. It is about probability, about understanding that some environments punish uncertainty more harshly than others. Antarctica does not offer second chances easily. What makes this avoidance especially interesting is that it exists alongside some of the most ambitious scientific efforts on Earth. Ice cores drilled kilometers deep, telescopes positioned to observe cosmic radiation with minimal interference, neutrino detectors embedded in ice so clear it behaves like glass. Scientists are not reluctant to work in Antarctica. They are selective. The places that remain untouched are not always the most dramatic or visually striking. Sometimes they are vast, featureless stretches where nothing seems to happen. But nothing in Antarctica often means nothing measurable with current tools. It does not mean stability. It does not mean safety. There are regions where the ice sits atop liquid water under immense pressure. Subglacial lakes sealed off from the surface for hundreds of thousands of years. Drilling into them risks contamination, not just of the lake, but of the scientific record itself. Introducing modern microbes into an ancient ecosystem would erase the very information scientists hope to learn from it. So these locations are approached slowly, cautiously, sometimes not at all, until methods improve. In other areas, the bedrock beneath the ice drops sharply, creating conditions where the ice sheet becomes unstable. These zones are known to contribute disproportionately to sea level rise when they change. Scientists monitor them constantly from a distance, but placing people or equipment directly on top of them introduces risks that are not always justified by the incremental gain in data. Avoidance in this context is not neglect, it is strategy. And then there is the simple reality of scale. Antarctica is enormous, larger than Europe, larger than Australia. Even with unlimited funding and perfect weather, it would take generations to visit every region in person. Choices have to be made. Some areas become hubs of activity. Others remain quiet, watched from afar, waiting for a reason strong enough to justify closer contact. As we continue, we'll move deeper into the specific reasons certain zones remain off-limits. Not in the sense of official bans or hidden agendas, but in the quieter language scientists use among themselves. Places where instruments behave strangely, where ice behaves less like ice, where effort and outcome drift further apart the longer you stay. For now, let that image settle. A continent that isn't resisting exploration exactly, but shaping it, allowing some questions to be asked up close, and others only from a careful distance. Antarctica has a way of unsettling expectations long before anyone sets foot on it. On a globe, it looks passive, a clean white shape at the bottom of the world, quietly holding the planet in place. On satellite images, it appears static, frozen in time, a continent that has finished its story and settled into silence. But this impression dissolves the moment you start listening to the people who work there, not the dramatic storytellers or headline writers, but the scientists who return year after year with the same calm conclusion. Antarctica does not like to be fully known. This is not because it hides itself in any intentional way. There is no secrecy built into the ice, no deliberate obstruction. The refusal is subtler than that. It comes from scale, motion, and indifference. Antarctica does not respond to curiosity. It does not reward persistence. It simply continues doing what it has always done, regardless of who is watching. Unlike other continents, Antarctica offers very few reference points. No cities, no roads, no permanent landmarks that remain unchanged for long. Even mountains, when they appear, are often partially buried, their outlines softened by centuries of snowfall. The ice sheet covers nearly everything, and that ice is not a static layer. It is a living system, moving slowly under its own weight, flowing outward from the centre toward the sea. The continent is constantly rearranging itself, but at a pace that is easy to underestimate. This movement alone complicates understanding. When scientists map Antarctica, they are not mapping solid ground in the traditional sense. They are mapping thickness, velocity, temperature gradients, and pressure. The surface is only the top of a structure that can extend kilometres downward. What lies beneath is often inferred rather than directly observed. Radar pulses bounce back from layers in the ice. Gravity measurements hint at hidden valleys and ridges. Seismic waves reveal textures deep below the surface, but inference is not the same as certainty. There are large portions of Antarctica where the bedrock has never been seen directly, not photographed, not sampled, not touched. Drilling through kilometres of ice is possible, but it is slow, expensive, and limited to carefully chosen locations. Every borehole is a major operation, requiring years of planning, strict contamination controls, and constant monitoring. Even then, the ice itself can behave unpredictably, deforming around equipment, closing holes, or shifting pressure in ways that make continued work impossible. This means that Antarctica remains, in a very real sense, partially theoretical. Scientists know it exists. They know roughly how it behaves. But many of its internal structures are known only through models that must constantly be revised as new data arrives. And new data arrives unevenly, clustered around research stations and transit routes, leaving vast interior regions comparatively silent. Silence in Antarctica is not absence. It is density without signal. One reason the continent resists being fully known is that it operates on timescales that don't align well with human observation. Many of the most important processes unfold over centuries or millennia: ice accumulation, ice flow, basal melting, subglacial erosion. These changes are slow enough that a human lifetime captures only a narrow slice. Instruments can record snapshots, but interpreting those snapshots requires assumptions about what came before and what will come after. Those assumptions are constantly challenged. In some regions, ice flow speeds up or slows down without an obvious trigger. In others, temperature profiles change subtly, hinting at processes happening far below the surface. Sometimes these changes contradict existing models. When that happens, scientists don't conclude that Antarctica is behaving incorrectly. They conclude that their understanding is incomplete. This incompleteness is not evenly distributed. Coastal areas are better studied. Regions near long-established stations are mapped in detail. Flight paths and overland routes are monitored carefully. But move away from these corridors, toward the interior plateau or into complex glacial systems, and certainty begins to thin out. Not because no one cares, but because each additional kilometre increases logistical complexity exponentially. Every expedition into Antarctica is constrained by weight, fuel, time, and weather. You cannot simply detour to investigate something interesting. Decisions are made months in advance, and once a route is set, deviation carries serious consequences. This means that some areas remain unexplored not because they are forbidden, but because they are inconvenient in ways that matter. Antarctica also resists being known because it does not offer immediate feedback. In many environments, experiments yield results quickly. Measurements confirm hypotheses or disprove them within manageable timeframes. In Antarctica, results often raise more questions than they answer. A temperature anomaly here, an unexpected ice thickness there, a subglacial lake behaving differently than predicted. Each discovery opens multiple avenues of uncertainty. There is also the problem of isolation. Antarctica is not just physically distant, it is operationally distant. Every piece of equipment, every person, every litre of fuel must be transported across vast distances, often through multiple stages. If something fails, replacement is not a short drive away. This reality shapes research priorities. Scientists choose projects that justify the effort. Some questions, no matter how interesting, are postponed simply because the environment makes them impractical at present. This practicality shapes knowledge in subtle ways. It means that Antarctica is not studied evenly or comprehensively. It is studied strategically. Areas that intersect with global climate models, sea level projections, or atmospheric measurements receive attention. Areas that do not immediately connect to pressing questions are observed indirectly or left for future generations with better tools. The continent also resists being known because it interacts with systems far beyond itself. Antarctic ice affects ocean circulation. It influences global weather patterns. It stores climate history in layered snowfall that predates human civilization. To understand Antarctica fully, one must understand these connections, and those connections extend across the entire planet. No single dataset can capture that complexity. Even when scientists collect pristine data, interpretation remains difficult. Ice cores record chemical signatures from ancient atmospheres, but translating those signatures into precise global conditions requires careful calibration. Ocean measurements near ice shelves reveal temperature and salinity changes, but linking those changes to specific ice dynamics involves multiple layers of modelling. Each step introduces uncertainty. Antarctica also challenges human intuition. Many of the processes that matter most are invisible. Heat transfer through ice, pressure-induced melting at the base of glaciers, microbial ecosystems sealed away from sunlight. These are not processes people can easily visualize or relate to everyday experience. As a result, understanding remains abstract. mediated through graphs and equations rather than direct observation. There is a psychological element to this resistance as well. Antarctica does not conform to narratives of conquest or mastery. There are no indigenous populations to learn from, no long history of human adaptation to draw upon. Every human presence there is temporary, artificial, dependent on constant support. This reinforces the sense that the continent does not belong to us in the way other places do. Even language struggles to capture Antarctica accurately. Terms like desert and wilderness fall short. Antarctica is technically a desert, but that label suggests barrenness rather than depth. It is a wilderness, but one defined not by abundance of life, but by the dominance of physical processes. The usual metaphors don't quite fit. This mismatch between expectation and reality contributes to the sense that Antarctica remains elusive. Each attempt to describe it simplifies something essential. Each map leaves something out. Each expedition returns with data that fits awkwardly into existing frameworks. And yet, this refusal to be fully known is not a failure. It is a characteristic. Antarctica operates under conditions that push against the limits of observation, patience, and interpretation. It forces science to slow down, to acknowledge uncertainty, to accept that some answers will arrive incrementally or not at all. This is why scientists speak about Antarctica differently. There is less confidence, more conditional language, fewer declarations, more caveats. Not because the work is weaker, but because the environment demands humility. As technology improves, more areas will become accessible, better satellites, more robust autonomous systems, improved drilling techniques. Antarctica will yield more information, but not all at once, and not evenly. There will always be regions that lag behind understanding, not because they are hiding, but because they exist at the edge of what current tools can resolve. In that sense, Antarctica does not resist being known actively. It simply does not adjust itself to human schedules or expectations. It does not care whether its processes are convenient to study or not. It unfolds according to its own rules, at its own pace. And that quiet mismatch between human urgency and Antarctic indifference is what gives rise to the feeling that this continent remains just beyond reach. Not mysterious in a dramatic sense, but persistently incomplete, always offering data, never offering closure. As we move forward, this tension becomes more apparent. The refusal to be fully known is not uniform across the continent. Some areas push back harder than others. Some regions introduce complications that go beyond scale and distance, entering realms where even well-tested instruments begin to falter. And it is there, in those specific zones, that avoidance shifts from inconvenience to intention, not as a retreat, but as a pause. From a distance, Antarctica looks simple. On most maps, it appears as a smooth white mass, featureless except for a few jagged coastlines, and the occasional mountain range poking through the ice, like a reminder that land exists underneath. This visual simplicity creates a powerful illusion. It suggests that Antarctica is empty, uniform, and largely passive, a place where nothing much happens unless someone goes there to make something happen. But that impression is one of the most persistent misunderstandings about the continent, and it quietly shapes how people think about exploration, science, and absence. The white map is not wrong, but it is deeply misleading. What the map shows is surface colour, not structure. It shows snow and ice, not depth, movement, pressure, or complexity. Antarctica is not a blank page. It is a densely layered system, stacked vertically rather than spread horizontally. Almost everything that matters is hidden beneath the surface, compressed under kilometres of ice, unfolding at scales that resist easy visualization. If you were to strip away the ice in your imagination, Antarctica would look nothing like the smooth shape we recognize. The bedrock beneath is fractured, mountainous, uneven, carved by ancient rivers and tectonic forces long before ice dominated the region. There are valleys deeper than the Grand Canyon, mountain ranges as large as the Alps, and basins that dip well below sea level. These features are real, but they are buried so deeply that they exist more as data points than landscapes. Because we cannot see them directly, they're often treated as abstract. Lines on charts, contours in models. But these hidden structures matter enormously. They influence how ice flows, where it accelerates, where it thins, and where it becomes unstable. They determine which glaciers retreat quickly and which remain stubbornly anchored. The illusion of a flat white surface hides the fact that Antarctica's behaviour is shaped from below as much as from above. Even the ice itself is not uniform. Snow accumulates differently depending on wind patterns, temperature gradients, and subtle changes in elevation. Over time, these layers compress into ice, trapping tiny air bubbles that preserve snapshots of ancient atmospheres. Each layer is a record, but those records are not evenly distributed. In some places, accumulation is rapid. In others, it is slow or interrupted. This means the climate history stored in the ice varies dramatically from one location to another. A white map suggests sameness. Antarctica is anything but. Movement is another element erased by the illusion. Ice is often imagined as frozen solid, static and inert. In reality, the Antarctic ice sheet is constantly in motion. It flows outward from the interior toward the coast, driven by gravity and pressure. This movement is slow by human standards, measured in meters per year rather than kilometers per hour, but its effects are enormous. Over time, it reshapes the continent, redistributes mass, and interacts with the surrounding ocean in ways that affect global sea levels. On a map, none of this motion is visible. There are no arrows showing ice velocity, no shading to indicate stress zones or shear margins. Without those cues, it is easy to assume that nothing is happening. But scientists know that some of the most dynamic regions on Earth are hidden beneath that uniform white. The illusion of emptiness also obscures the presence of water. Beneath the ice sheet, liquid water exists in surprising abundance. Subglacial lakes, rivers, and wetlands are kept liquid by geothermal heat and pressure. Some of these systems have been isolated from the surface for hundreds of thousands, possibly millions of years. They form a hidden hydrological network that influences ice flow from below, lubricating the base of glaciers and altering how ice responds to stress. These water systems are not evenly distributed. They cluster in certain regions, often where the bedrock geometry and heat flow align just right. But because they are invisible at the surface, maps do not reveal them. A blank white area might conceal a complex dynamic environment beneath, one that plays a critical role in the continent's stability. The map also hides the atmosphere's influence. Antarctica is not just shaped by ice and rock, it is shaped by wind. Persistent, powerful winds sweep down from the interior, sculpting snow into hard, polished surfaces called sastrugi. These formations affect travel, accumulation, and even the interpretation of satellite data. Wind redistributes snow unevenly, creating zones of erosion and deposition that complicate surface measurements. From above, these patterns blur into uniformity. The white map smooths over texture, removing the evidence of constant interaction between ice and air. Another layer of complexity erased by the illusion is time. Maps present a snapshot, a fixed image that implies stability. Antarctica, however, is anything but static. The ice sheet responds to climate changes over long timescales, but it can also react abruptly when thresholds are crossed. Ice shelves can thin gradually for decades and then collapse within weeks. Glaciers can retreat slowly and then suddenly accelerate. These transitions are not visible on a static map. They require time series data, repeated measurements, and careful interpretation. Without that context, the continent appears unchanging, reinforcing the idea that unexplored areas are simply empty spaces waiting to be filled. The illusion of emptiness also affects how people think about access. When a place looks blank, it seems approachable. The absence of visible obstacles suggests ease of movement. But in Antarctica, the lack of visual cues is itself a hazard. Crevasses are often hidden beneath thin snow bridges. Ice thickness can vary dramatically over short distances. What looks like solid ground may be underlain by voids, fractures, or moving ice streams. On a map, these dangers do not appear. There are no warning symbols for instability, no markers for stress zones. This disconnect between appearance and reality is one reason scientists approach certain regions cautiously. They know that the map does not tell the full story, and that assumptions based on surface uniformity can be costly. The idea of emptiness also downplays the presence of life. Antarctica is often described as lifeless, but that is another simplification. Life exists there in forms adapted to extreme conditions. Microbial communities thrive in ice, snow, and subglacial environments. Algae bloom on the undersides of sea ice. Bacteria survive in briny channels within the ice itself. These organisms play roles in biogeochemical cycles that scientists are only beginning to understand. Because this life is microscopic and often hidden, it does not register on maps or photographs. The continent looks sterile, reinforcing the sense that nothing is happening. But at small scales, activity is constant. This illusion has consequences for science. When a place is perceived as empty, it is easier to overlook its complexity. It becomes tempting to treat large regions as interchangeable, to assume that data from one area can stand in for data from another. In Antarctica, this assumption often fails. Small differences in conditions can lead to large differences in behaviour. Scientists are acutely aware of this, which is why they are careful about extrapolation. A measurement taken in one location may not apply elsewhere. A model that works well for one glacier may fail completely for another. The white map encourages generalization. The reality demands specificity. The illusion also shapes public imagination. Antarctica becomes a backdrop rather than a subject, a stage for exploration stories, heroic endurance, or abstract climate narratives. While these stories have their place, they can obscure the everyday scientific reality, which is slower, quieter, and more uncertain. In practical terms, the illusion of emptiness influences where research happens. Areas near established stations are studied more intensively because access is easier and logistics are manageable. Vast interior regions remain less explored not because they lack importance, but because the map does not convey what would be required to work there safely and effectively. This creates uneven knowledge. Some areas are densely studied, their processes relatively well constrained. Others remain data poor, their behaviour inferred rather than measured. The white map hides this unevenness, presenting a false sense of coverage. It also hides failure, instruments lost, experiments abandoned, routes deemed too unstable to continue. These stories rarely make it into public-facing representations. The map remains clean, unmarked by the quiet decisions that shape scientific practice. In reality, Antarctica is full of invisible boundaries, zones where ice flow changes regime, regions where temperature gradients become unpredictable, areas where underlying geology introduces instability. Scientists learn these boundaries not by seeing them on a map, but by encountering their effects, often indirectly. Over time, these experiences accumulate into a collective understanding. Certain regions acquire reputations within the scientific community, not as forbidden places, but as areas where caution is warranted, where effort does not reliably translate into insight. These reputations are based on experience, data, and sometimes loss. The illusion of an empty white map does not capture any of this. It suggests potential without cost. It implies openness without resistance. Antarctica quietly contradicts both assumptions. As technology improves, the map becomes more detailed. Satellite data adds layers of information. Models become more refined. But even the most advanced representations remain abstractions. They compress complexity into symbols and colours, useful but incomplete. Understanding Antarctica requires holding two ideas at once. From a distance, it looks simple. Up close, it is anything but. The challenge is remembering that the simplicity is an artifact of perspective, not a property of the place itself. As we continue, this mismatch between appearance and reality becomes more consequential. The regions scientists avoid are often those where the illusion breaks down most dramatically, where the white surface conceals dynamics that resist measurement, prediction, or control. And it is there, beyond the reassuring emptiness of the map, that the limits of exploration become most apparent. When people hear that parts of Antarctica remain unexplored, the word itself tends to fill in the gaps. Unexplored sounds like blankness. It suggests mystery in the simplest sense, places no one has seen, no one has touched, no one has measured. It invites images of untouched ground and unanswered questions waiting patiently for someone to arrive. But in scientific language, unexplored does not mean unobserved, and it certainly does not mean ignored. In Antarctica, some of the most carefully studied regions are also the ones no human has ever stood on. This distinction matters because it reshapes how avoidance is understood. Scientists are not staying away from certain areas because they know nothing about them. Often they stay away precisely because they know enough. Antarctica has been watched from above for decades. Satellites track changes in ice thickness, surface elevation, temperature, and motion with remarkable precision. Radar instruments penetrate ice and reflect back information about internal layers and the bedrock below. Gravimetric measurements reveal mass distribution. Seismic waves generated by distant earthquakes pass through the continent and return clues about its internal structure. In many cases, scientists can describe what is happening in a region without ever going there in person. This is where the idea of unknown begins to fracture. A place can be unmapped in the traditional sense and still be richly described in data. It can be inaccessible on foot and yet central to global models. It can resist human presence while remaining scientifically visible. Some of the most important discoveries about Antarctica have come from places no one has visited. Vast ice streams were identified from space before they were ever approached on the ground. Subglacial lakes were inferred from radar reflections long before drilling was even considered. Entire drainage systems beneath the ice were mapped without a single footprint left behind. So when scientists refer to a region as unexplored, they're usually talking about physical presence, not informational absence. There are practical reasons for this. Direct exploration is expensive, slow, and risky. It requires infrastructure, fuel, trained personnel, and contingency plans for emergencies that may not be solvable quickly. Indirect observation, by contrast, can be continuous and relatively safe. Satellites do not suffer frostbite. They do not fall into crevasses. They do not need evacuation when storms roll in. As a result, Antarctic science has developed a layered approach to knowledge. Remote sensing comes first. Models are built and tested. Patterns emerge. Only then, if the potential benefit outweighs the cost and risk, do scientists consider sending people or equipment into the field. Many areas never pass that threshold, not because they lack importance, but because the information gained from direct contact would be marginal compared to what is already known indirectly. In this context, unexplored becomes a misleading shorthand. It implies a lack of curiosity that simply does not exist. There are regions of Antarctica that scientists know are unstable. Ice there moves in complex ways, influenced by underlying water systems and bedrock geometry. Models show that these areas play an outsized role in future sea level rise. They are monitored constantly from space. Their behaviour is analysed in detail. But sending teams into these zones would expose them to extreme risk, with little guarantee of improved understanding. The data collected remotely is already sufficient for many purposes. Avoidance here is not ignorance, it is restraint. Another reason unexplored does not mean unknown is that Antarctica operates as a connected system. changes in one region often influence others. Ice flow patterns propagate. Ocean currents interact with ice shelves far from where they originate. Atmospheric conditions link distant parts of the continent. This means scientists can learn about one area by studying its effects elsewhere. For example, thinning at the edge of an ice shelf may indicate processes occurring deep inland. Acceleration of a glacier may reflect changes at its base hundreds of kilometers away. By observing these outcomes, scientists infer what is happening upstream, even if they never set foot there. This inferential approach is common in many sciences, but in Antarctica it is often the only feasible one. There is also a historical dimension to this knowledge. Antarctica has been studied for over a century. Early expeditions mapped coastlines, measured temperatures, and recorded weather patterns. Over time, this patchwork of observations grew into a foundation upon which modern science builds. Even areas that have not been revisited recently are not blank slates. They are part of a long observational record. This record includes failures as well as successes, attempts to traverse certain regions that ended early, instruments that did not survive long enough to return useful data, routes that proved too unstable to repeat. These experiences contribute to collective understanding. They inform decisions about where to focus effort and where to pause. In this way, Antarctica accumulates a kind of negative knowledge, information about what does not work, what is not sustainable, what introduces unacceptable risk. This knowledge is rarely visible to the public, but it is deeply embedded in scientific planning. There are also ethical considerations that shape exploration. Some unexplored regions contain environments that have been isolated for extraordinary lengths of time. Subglacial lakes sealed beneath ice for hundreds of thousands of years may host unique microbial life. Introducing modern contaminants could permanently alter these ecosystems. Scientists are acutely aware of this risk. As a result, many of these environments are studied indirectly for years, sometimes decades, before any direct sampling is attempted. In some cases, direct access is postponed indefinitely. The decision is not driven by lack of interest, but by a recognition that the act of exploration itself can destroy what is being studied. Here again, unexplored does not mean unknown. It means deliberately untouched. The language used to describe Antarctica often struggles to capture this nuance. Popular narratives favour discovery and firsts: the first crossing, the first drilling, the first measurement. But much of Antarctic science advances quietly, through refinement rather than revelation, through better models, longer data sets, and improved interpretation of signals that were already there. This can make avoidance look like stagnation from the outside. In reality, it is often the opposite. It reflects a mature understanding of the system, one that recognises diminishing returns and prioritises long-term insight over immediate presence. There are also political and logistical frameworks that shape what counts as exploration. Antarctica is governed by international agreements that emphasise peaceful use and scientific cooperation. Research activities are coordinated to minimise environmental impact. This means that not every technically possible expedition is approved or encouraged. Choices are made collectively, based on shared priorities and constraints. In this environment, unexplored regions are not waiting for bold individuals. They are part of a negotiated landscape of attention and restraint. It is also worth noting that some areas remain unexplored simply because they offer little additional information at present. Not every region contributes equally to scientific questions. Some areas are relatively stable, their behaviour well captured by existing models. Others are dynamic and uncertain. Resources are finite. Scientists focus where uncertainty intersects with consequence. This focus shifts over time. Areas once considered low priority may become central as conditions change or new questions emerge. Conversely, regions that were once the subject of intense interest may fade into the background as understanding solidifies. The map of exploration is therefore not static. It reflects evolving knowledge, technology, and values. The idea that unexplored means unknown persists because it aligns with older models of exploration, where physical presence was the primary path to understanding. Antarctica has quietly overturned that model. It has shown that distance does not always equal ignorance, and that proximity does not guarantee insight. This does not mean that direct exploration is obsolete. Far from it. Ground-based measurements remain essential for validating models and interpreting remote data. Ice cores in particular require physical access, but it does mean that presence is no longer the default goal. It is one tool among many, used selectively. As we continue, this selective approach becomes even more pronounced. Some regions are not just unexplored, but actively avoided, not because they are unknown, but because what is known about them makes caution the wiser choice. These are places where data already suggests instability, unpredictability, or disproportionate risk. Places where the cost of knowing a little more may be far greater than it appears on a map, and it is there, in that quiet gap between curiosity and consequence, that Antarctica most clearly defines the limits of exploration. Distance in Antarctica is not measured the same way it is elsewhere. On most continents, distance is something you plan around. You calculate travel time, fuel, rest stops. You assume that if something goes wrong, help exists somewhere beyond the horizon. In Antarctica, distance behaves more like a condition than a number. It presses in on every decision, stretching simple tasks into logistical chains and turning minor delays into serious concerns. When scientists talk about avoiding certain regions, distance is often the first factor mentioned, not because it is dramatic, but because it quietly shapes everything that follows. Antarctica is vast in a way that resists intuition. It is not just large in area, but expansive in emptiness. There are no towns to pass through, no alternate routes, no gradual transitions from inhabited to uninhabited space. Once you leave a research station, you are immediately and completely on your own. Every kilometre increases separation not only from people, but from infrastructure, from supplies, from the possibility of improvisation. This separation changes how problems are defined. In most places, equipment failure is an inconvenience. In Antarctica, it can be the end of an expedition. A broken vehicle cannot be towed easily across ice. A failed generator cannot be replaced unless another one was already brought along. Even small malfunctions become significant when the nearest help may be hundreds or thousands of kilometres away, reachable only by aircraft that depend on weather conditions you cannot control. Cold amplifies this distance. It does not simply make things uncomfortable. It alters materials, chemistry, and time. Metals become brittle. Plastics lose flexibility, batteries drain faster, lubricants thicken, electronics behave unpredictably. Even the air itself becomes denser, changing how engines perform and how sound travels. For humans, cold narrows attention. It reduces dexterity. Tasks that are trivial at room temperature become slow and deliberate. Gloves make fine motor control difficult. Exposed skin risks injury within minutes. Decision-making suffers as the body prioritizes heat retention over cognitive clarity. None of this is dramatic in the moment. It accumulates quietly, eroding efficiency and increasing the likelihood of small mistakes. These effects compound with distance. The farther a team travels from support, the longer they are exposed to conditions that degrade both equipment and judgment. Each additional day in the field increases wear and uncertainty. This is why some areas, though scientifically interesting, are approached reluctantly. The cost of simply being there can outweigh the value of the data collected. Silence adds another layer. Antarctica is one of the quietest places on Earth, but not in a peaceful sense. The silence is expansive, absorbing. It removes familiar cues. Without trees, animals, or human activity, sound does not behave as expected. Wind can carry noise over long distances or swallow it entirely. Engines, when they run, sound isolated and fragile against the vastness. This silence affects communication. Radios are essential, but they rely on power and atmospheric conditions. Signals can degrade or disappear. There are areas where communication with satellites is intermittent, creating periods where teams are effectively alone, unable to send or receive information. This is not a constant state, but its possibility shapes planning. Silence also affects perception of time. Without daily rhythms of sound and activity, days blur together. Light conditions may remain unchanged for weeks or months. The body's internal clock struggles to anchor itself. Fatigue becomes harder to recognize. This cognitive drift is subtle, but in an environment where awareness matters, it is another factor that pushes scientists to limit exposure. Distance, cold, and silence reinforce one another. Cold slows movement, making distances feel longer. Distance prolongs exposure to cold. Silence removes feedback that might otherwise signal trouble early. Together they create an environment where errors propagate quietly, often unnoticed until correction is difficult or impossible. This is why Antarctica is planned rather than explored spontaneously. Routes are chosen with care, timelines include buffers, redundancy is built into every system. Even so, uncertainty remains. Weather forecasts are probabilistic, not guarantees. Ice conditions change. Equipment ages faster than expected. Plans are revised, sometimes abandoned, not because of dramatic failure, but because risk slowly accumulates beyond acceptable limits. Certain regions intensify these factors. The interior plateau, for example, is not only far from the coast, but also extremely cold and elevated. Air is thinner. Temperatures remain low year-round. Winds can be persistent. The lack of surface features makes navigation more difficult, increasing reliance on instruments that may themselves be affected by the cold. In such places, the silence is profound. There are no visual landmarks to break the horizon, no sound except wind and machinery. For scientists, this isolation is both a challenge and a signal. It reminds them that they are operating at the edge of practical human presence. Beyond that edge, even well-prepared teams may find themselves overstretched. Distance also affects rescue. In most environments, emergency response is a matter of hours. In Antarctica, it can take days or weeks. Aircraft cannot fly in all conditions. Landing sites require preparation. Crews must be available. Fuel must be staged. A rescue mission introduces its own risks, sometimes exceeding those faced by the original team. This reality weighs heavily on decision-making. Scientists are trained to assess risk objectively, but they are also aware that their choices affect others. Venturing into regions where rescue would be difficult or impossible is not taken lightly. Avoidance, in this sense, is an ethical choice as much as a logistical one. Cold complicates rescue further. Injuries behave differently in low temperatures. Healing slows. Equipment used in medical care may not function as intended. Evacuation itself exposes patients to cold stress. The margin for successful intervention narrows. Silence again plays a role. Without constant communication, delays in reporting problems can occur. A missed check-in may be the first sign that something is wrong, but by then, distance and weather may already limit response options. These constraints are not theoretical. They are informed by experience. Over decades, Antarctic programs have accumulated detailed records of incidents, near misses, and lessons learned. Patterns emerge. Certain combinations of distance, cold, and isolation correlate strongly with increased risk. When these factors align in particular regions, those regions acquire a reputation within the scientific community. This reputation is not based on fear or myth. It is based on probability, on the recognition that some environments offer diminishing returns for increasing exposure. Scientists do not need to be physically present everywhere to understand this. It is also important to note that distance in Antarctica is not just horizontal. Vertical distance matters too. drilling through ice, descending into crevasses, or accessing subglacial environments introduces new dimensions of separation. Once equipment or people move below the surface, retrieval becomes more complex. Cold and silence intensify in enclosed spaces. Communication becomes harder, time becomes more expensive. These vertical distances are often invisible on maps, but they are central to decisions about exploration. A region with deep ice, complex internal structure, and poor surface stability may be avoided not because it is far away, but because accessing it safely would require overcoming multiple layers of distance at once. Technology mitigates some of these challenges, but it does not eliminate them. Autonomous systems reduce human exposure, but they still depend on power, communication, and recovery. When a robot fails in a remote region, distance and cold still determine whether it can be retrieved or repaired. Silence still limits real-time diagnosis. As a result, scientists often prefer to observe from afar, using tools that allow continuous monitoring without constant presence. This approach respects the realities of the environment. It acknowledges that some places exert pressures that cannot be fully neutralized by planning or equipment. The problem of distance, cold, and silence is not a barrier to knowledge. It is a filter. It shapes which questions are asked directly, and which are approached indirectly. It encourages patience and selectivity. It reminds researchers that presence is not always the most effective path to understanding. As we move onward, these factors become intertwined with others that further complicate exploration. In some regions, the physical challenges are joined by environmental behaviours that defy prediction. Places where instruments fail not just because of cold, but because the environment itself behaves in unexpected ways. It is there that avoidance shifts from caution to necessity, and where the limits imposed by distance, cold, and silence are tested most clearly. There are places in Antarctica where the environment does not simply challenge instruments. It overwhelms them in quiet, persistent ways that leave no clear point of failure. Nothing dramatic announces itself. No alarms, no explosions, no sudden catastrophe. Devices are deployed carefully, tested thoroughly, and monitored as long as conditions allow. Then, gradually or sometimes abruptly, the data stream thins, distorts, or stops altogether. Not because the technology was poorly designed, but because the assumptions behind its design no longer hold. Scientific instruments are built with limits in mind. Temperature ranges, pressure tolerances, expected rates of change. Antarctica stretches all of those limits, but certain regions push beyond them entirely. These are the places scientists learn about not from success, but from repeated, consistent malfunction. One of the most common problems is cold-induced drift. At extreme temperatures, materials behave differently at a molecular level. Electrical resistance changes, mechanical components contract, sensors calibrated under laboratory conditions begin to shift, not enough to trigger obvious faults, but enough to skew results. In regions where temperatures remain far below design thresholds for long periods, this drift becomes cumulative. Data becomes unreliable long before instruments fail outright. This creates a difficult situation. An instrument that produces incorrect data is often more dangerous to science than one that stops completely. Detecting subtle failure requires cross-referencing multiple sources, and in remote Antarctic regions, redundancy is limited. When scientists notice inconsistencies they cannot resolve remotely, they face a choice. Attempt retrieval, which may be risky or impossible, or abandon the instrument and discount its output. In some regions, this has happened often enough that new deployments are no longer considered worthwhile. Power is another limiting factor. Batteries lose capacity rapidly in extreme cold. Even specialized cold weather batteries degrade faster than expected when temperatures remain low for months without interruption. Solar power is unreliable during the long Antarctic winter, when darkness persists for weeks or months. Wind power introduces mechanical complexity and vulnerability to icing and fatigue. Instruments placed far from stations often rely on a combination of power sources, all of which are stressed simultaneously. When power drops below a certain threshold, systems may shut down gracefully, or they may fail unpredictably. Restarting remotely is not always possible. In some cases, instruments enter states they were never programmed to recover from, trapped between operational modes, slowly draining their remaining energy. Communication failures compound the problem. Many instruments depend on satellite links to transmit data. At high latitudes, satellite coverage is uneven. Orbits create gaps where communication windows are brief or non-existent. Atmospheric conditions can interfere with signal strength. In some regions, instruments are effectively isolated for long stretches, unable to report their status. This isolation means that failure often goes unnoticed until long after it occurs. By the time scientists realize an instrument has stopped working, conditions on the ground may have changed dramatically. Snow accumulation can bury equipment. Ice movement can shift it. Retrieving or repairing it may no longer be feasible. Some of the most problematic regions are those where ice dynamics introduce additional stress. Ice streams, shear zones, and areas of differential movement place constant mechanical strain on anything embedded in or resting on the surface. Even small amounts of movement can twist cables, misalign sensors, or introduce microfractures that propagate over time. In these regions, instruments may function perfectly for weeks or months, only to fail suddenly when accumulated stress crosses a threshold. From the outside, this can look like random failure. In reality, it is the result of slow, continuous forces acting below the level of immediate detection. Electromagnetic interference presents another challenge. Certain areas of Antarctica exhibit unusual magnetic behavior due to geological structures beneath the ice and the continent's position relative to Earth's magnetic field. Instruments that rely on magnetic orientation or sensitive electronic measurements can behave erratically. Calibration becomes difficult. Readings fluctuate in ways that are hard to distinguish from genuine signals. Scientists are aware of these effects, but compensating for them requires detailed local knowledge. In regions that are already difficult to access, gathering that knowledge becomes a circular problem. You need reliable instruments to understand the environment, but the environment prevents reliable instrumentation. Mechanical systems face their own set of issues. Moving parts are especially vulnerable. Lubricants thicken or freeze. Bearings wear unevenly. Materials that perform well in other cold environments degrade under prolonged Antarctic conditions. Even simple mechanisms like hinges or actuators can seize without warning. For this reason, many Antarctic instruments are designed to minimize moving parts. But in some applications, movement is unavoidable. Drilling systems, sampling mechanisms, rotating sensors. In regions where failure rates have been consistently high, scientists have learned to avoid deploying such systems altogether. There are also areas where the ice itself interferes with measurement in unexpected ways. Variations in density, crystal structure, and impurity content can affect how radar and seismic signals propagate. In some regions, internal layering is so complex that signals scatter or attenuate unpredictably. Data becomes noisy, ambiguous, or misleading. These are not failures of the instruments, but limitations imposed by the medium. Interpreting such data requires assumptions that may not hold locally. When uncertainty becomes too large, the scientific value of the measurement declines. Environmental noise adds another layer. Wind-induced vibration, thermal cracking, ice deformation. These processes generate signals that can overwhelm sensitive instruments. Seismometers, for example, are designed to detect subtle ground motion. In certain Antarctic regions, background noise levels are so high or so irregular that distinguishing meaningful signals becomes extremely difficult. Attempts have been made to isolate instruments from this noise, burying them deeper, shielding them, adjusting sensitivity. In some places these measures work, in others the noise persists, driven by processes that cannot be easily dampened. There are also biological factors, though they are less obvious. Microbial activity within ice can affect chemical sensors. Brine channels can alter conductivity measurements. These effects are subtle, but in environments where signals are already weak, they matter. Over time, patterns emerge. Certain regions produce higher rates of instrument failure, lower data quality, and greater uncertainty. Scientists track these patterns carefully. They compare notes across programs and countries. Decisions about future deployments are informed by this collective experience. When a region is repeatedly associated with unreliable instrumentation, it becomes a low priority for direct measurement. Not because it lacks scientific interest, but because the tools required to study it do not perform as needed. Until technology advances or conditions change, these areas remain observed indirectly. This avoidance is often invisible to those outside the scientific community. Public narratives tend to focus on discovery and innovation, not on the quiet recognition of limits. But within Antarctic research, knowing where instruments stop working is as important as knowing where they succeed. It informs risk assessments, budget allocations, mission design. It shapes the questions scientists choose to pursue and the methods they use. In this way, instrument failure becomes part of the knowledge base, not an embarrassment, but a guide. There is also a psychological aspect. Repeated failure can erode confidence in certain approaches. Teams become cautious. They refine their expectations. They shift focus to regions where effort is more likely to yield reliable results. This is not a retreat, but an adaptation. It is important to understand that these problematic regions are not static. Ice movement changes. Climate conditions evolve. What is inaccessible today may become more stable in the future, or vice versa. Scientists revisit their assumptions regularly, updating maps of reliability as new data becomes available. Technological progress also shifts boundaries. Instruments designed for harsher conditions, better power management, more robust communication may eventually succeed where earlier ones failed. But each deployment carries cost and risk. Until confidence is high enough, restraint remains the default. In some cases, scientists deliberately place experimental instruments in these challenging regions, fully expecting failure. These deployments are designed not to collect long-term data, but to test limits, to learn how and why systems break. This information feeds back into design improvements. Even so, there are areas where failure is so consistent that further testing is postponed. The environment there is not hostile in a dramatic sense. It simply does not align with current technological capabilities. It operates on its own terms. These places occupy a peculiar status in Antarctic science. They are not unknown. They are not ignored. They are recognized as zones where the interaction between environment and instrumentation produces diminishing returns, where effort dissolves quietly into noise and uncertainty. As we continue, this pattern becomes more pronounced. Instrument failure is often a symptom of deeper dynamics at play, ice that behaves differently than expected, subsurface processes that defy simple models, regions where the continent's internal complexity expresses itself most strongly. It is in those regions that avoidance becomes a form of respect, not for mystery, but for the limits of current understanding. Ice is usually imagined as the opposite of motion, solid, fixed, locked in place. In everyday life, ice either stays where it is or breaks suddenly and dramatically. It does not drift, it does not flow. And yet, across much of Antarctica, ice behaves less like frozen ground and more like a very slow, very heavy ocean. It moves continuously, reshaping the continent from the inside out, and it does so in ways that make certain regions deeply impractical for direct study. This movement is not subtle in its consequences, even if it is subtle in speed. Measured from moment to moment, Antarctic ice appears still. Measured over months, years, or decades, it reveals itself as restless. Entire sections of the ice sheet slide, stretch, compress, and reorganize, driven by gravity, pressure, temperature, and the hidden landscape beneath them. Scientists understand this motion well enough to model it, but standing on it, building on it, or placing delicate instruments within it is another matter entirely. The Antarctic ice sheet is not a single, uniform mass. It is a complex system made up of slow-moving interior ice, faster-moving ice streams, and floating ice shelves at the coast. Each part behaves differently, and transitions between them are often abrupt. An area that looks stable on the surface may sit only a short distance from a zone of intense deformation, where ice accelerates and strains like taffy being pulled apart. Ice streams are the clearest example of this ocean-like behaviour. These are corridors of ice that move significantly faster than the surrounding sheet, sometimes hundreds of meters per year. They function like currents, draining ice from the interior toward the sea. From above, they can be identified by subtle surface features and satellite measurements of velocity. From the ground, however, their boundaries are not always obvious. The problem is that ice streams do not have hard edges. There is no visible line where slow ice ends and fast ice begins. Instead, there are shear zones, areas where ice deforms intensely as neighbouring sections move at different speeds. These zones are mechanically unstable. Crevasses form and heal. Stress builds and releases. The surface may look smooth one season and fracture the next. For scientists, these are difficult places to work. Any structure placed on moving ice is subject to distortion. Poles tilt, cables stretch, foundations shift. Instruments that rely on precise alignment lose calibration. Even GPS markers designed to track motion can be carried along faster than anticipated or rotated in ways that complicate interpretation. Drilling in such environments is particularly challenging. Boreholes through ice are not static voids. Ice flows inward, slowly closing the hole. In fast-moving regions, this closure happens more quickly. Equipment can become trapped. Sensors lowered into the ice may be crushed or displaced as the surrounding material deforms. Recovering them may be impossible. The ocean-like behaviour of ice is also influenced by what lies beneath. In many regions, the base of the ice sheet is lubricated by water. Pressure and geothermal heat melt ice at the bottom, creating thin films or channels of liquid water. This lubrication allows ice to slide more easily over bedrock, increasing speed and variability. These basal conditions are uneven. Some areas are relatively dry and slow-moving. Others are wet and dynamic. Transitions between them can occur over short distances, and they are not always stable over time. A region that is slow today may accelerate tomorrow if basal conditions change. From a scientific perspective, this variability is fascinating. From a logistical perspective, it is a serious complication. Floating ice shelves add another layer of complexity. These shelves are extensions of the ice sheet that float on the ocean, while remaining attached to land-based ice. They flex with tides. They respond to ocean temperatures below. They fracture, thin, and sometimes collapse. The motion here is three-dimensional, influenced by forces from above and below. Working on ice shelves means dealing with a surface that moves not just horizontally, but vertically. Tidal flexing can stress structures. Cracks can propagate unexpectedly. Areas that appear solid may be undercut from below by warmer water. Instruments placed on ice shelves face risks that do not exist inland. Because of this, some ice shelves and their upstream feeding regions are monitored almost entirely from a distance. Satellites provide velocity fields. Radar reveals thinning. Oceanographic measurements are taken at safer margins. Direct access is limited to carefully chosen sites, where conditions are better understood. The slow ocean of ice also complicates navigation. Routes that were safe one year may become hazardous the next. Snow bridges over crevasses shift. Stress patterns migrate. Markers placed to indicate safe passages must be checked and rechecked. In some regions, maintaining a route becomes more work than the scientific objective it serves. This is why certain areas are quietly avoided. Not because they are unknown, but because their internal motion introduces too much uncertainty. Planning becomes speculative. Timelines stretch. Risk increases without a corresponding increase in knowledge. It is important to understand that this movement is not chaotic. Ice follows physical laws. Its flow can be modelled and predicted within limits. Scientists can say with confidence that a given region will continue to move in a certain direction at roughly a certain speed. But roughly is not sufficient when placing people and equipment in harm's way. Small deviations matter. A change of a few meters per year can alter stress distribution enough to change surface conditions. A slight increase in basal water can accelerate flow locally. These changes are often invisible until their effects appear, and by then, adjustment may be difficult. The ocean analogy is useful here. Just as sailors respect currents even when the sea appears calm, Antarctic scientists respect ice flow even when the surface looks stable. You would not anchor a delicate structure in a strong current without constant adjustment. The same principle applies here. There is also a temporal challenge. Ice flow is continuous. It does not pause for field seasons. Instruments deployed in moving ice are always on borrowed time. They may work long enough to collect valuable data, or they may be compromised before their mission is complete. Planning must account for this uncertainty. Some experiments are designed to embrace motion. GPS networks measure how ice moves. Strain gauges record deformation. In these cases, movement is the signal. But for many other types of measurement, motion is noise, something that obscures the phenomenon of interest. This distinction influences where scientists choose to work. Regions with slow, predictable flow are preferred for long-term installations. Areas with complex or rapidly changing dynamics are studied indirectly or intermittently. The slow ocean of ice sets boundaries on practicality. There is also the issue of scale. Ice does not move uniformly across a region. Local variations matter. 2 points a few kilometers apart may experience very different conditions. Extrapolating from one to the other can lead to error. This makes sparse data particularly risky in dynamic zones. As a result, some regions remain undersampled by design. Scientists acknowledge their importance, but they wait. They refine models. They improve remote sensing. They develop instruments better suited to motion. Until then, restraint is the rational choice. The public often hears about dramatic ice events, shelves collapsing or glaciers accelerating. These stories give the impression that change is sudden and obvious. In reality, much of the motion is gradual, detectable only through careful measurement. It is this quiet persistence that makes it so challenging. Standing on Antarctic ice, it is easy to forget that you're on something that is moving at all. The horizon does not shift. Landmarks, if they exist, seem fixed. And yet, beneath your feet, forces are at work that will carry that ice and everything on it toward the sea. Scientists are keenly aware of this. They plan accordingly. They choose their battles. They accept that some parts of the continent are better left to instruments that can observe from afar, or to models that integrate multiple data sources without requiring constant presence. The slow ocean of ice is not an obstacle to understanding Antarctica. It is one of its defining features. But it is also a reminder that not all environments are equally compatible with human methods of inquiry. Some require patience, some require distance, and some, at least for now, ask to be watched rather than entered. As we continue, this moving ice connects directly to another challenge. In regions where flow interacts with terrain and weather, the surface itself can become unstable in ways that are difficult to predict. Equipment does not just drift, it disappears, and the reasons why led deeper into the continent's quieter hazards. There are places in Antarctica where loss does not look dramatic. Equipment is not smashed, buried in obvious collapse, or destroyed in a single visible event. Instead, it simply vanishes from usefulness. One season it is there, functioning, reporting data, marked carefully on maps. The next season it is gone, shifted beyond reach, buried too deeply, twisted beyond recovery, or rendered so inaccessible that retrieval no longer makes sense. These are the regions scientists describe, quietly and without exaggeration, as places that swallow equipment. This swallowing does not happen in a single way. It is the combined effect of ice motion, snow accumulation, structural stress, and time. Each process alone might be manageable. Together they create conditions where even well-designed, well-monitored instruments are gradually erased from practical existence. One of the simplest mechanisms is burial. Snowfall in Antarctica does not behave like snowfall elsewhere. It is often driven by wind rather than precipitation, redistributed continuously across the surface. In some regions, snow accumulates rapidly and unevenly, filling depressions, smoothing terrain, and covering anything left exposed. An instrument that stands half a metre above the surface one year may be completely buried the next, encased in compacted snow that quickly hardens into ice. This burial is not always predictable. Accumulation rates vary dramatically over short distances due to subtle changes in topography and wind patterns. An area that appears relatively stable may sit just downwind of a zone where snow is stripped away, becoming a natural collection point. Instruments placed there can be buried faster than models suggest, especially during winters when access is impossible. Once buried, recovery becomes difficult. Digging through meters of hardened snow and ice requires time, power, and specialized equipment. Even if retrieval is possible, the act of excavation can damage surrounding ice, destabilize the site, or compromise nearby instruments. In many cases, scientists make the decision to leave buried equipment in place, marking it as lost but accounted for. Another mechanism is horizontal displacement. As ice flows, anything resting on or embedded within it moves as well. Over time, instruments drift away from their original locations, sometimes slowly, sometimes faster than anticipated. GPS markers reveal this motion clearly, but not all equipment is designed to track its own movement. When an instrument shifts unexpectedly, it may end up in a region with very different conditions than those it was designed for. A sensor intended for stable ice may find itself crossing into a shear zone. A cable laid carefully across the surface may stretch and snap as neighbouring ice moves at different speeds. Anchors drilled into ice may rotate or tilt, altering orientation and stressing connections. None of this happens abruptly enough to trigger immediate alarms. It unfolds quietly, over months, until functionality degrades beyond usefulness. Crevasses introduce another form of loss. These deep fractures in the ice can open gradually, widen, narrow, or migrate. Some are visible and well mapped. Others are hidden beneath thin snow bridges. Equipment placed near crevasse fields is always at risk, even if initial surveys show solid ground. In some cases, crevasses form beneath equipment after deployment. Stress patterns in the ice change. A crack opens where none existed before. Instruments tilt, then drop, sometimes only a short distance, sometimes tens of meters into darkness. Retrieval from such depth is rarely attempted. The risk outweighs the benefit, and the exact location may be uncertain by the time the loss is detected. There are also regions where the ice itself deforms vertically. Surface elevation changes as ice flows over uneven bedrock or responds to changes in mass. An instrument anchored at a fixed depth may be slowly engulfed or exposed. Sensors designed to sit at the surface can end up buried. Subsurface instruments can be crushed or displaced as pressure changes. Water plays a role here as well. Meltwater at the surface can drain into cracks, refreezing and expanding, exerting force on anything nearby. At the base of the ice, liquid water lubricates motion, increasing variability. In some regions, subglacial water systems shift over time, altering stress distribution above. These changes propagate upward, affecting surface stability. From a distance, this all looks like loss without cause. An instrument stops reporting. Attempts to reconnect fail. Coordinates are checked, but when teams return months later, the site looks different. Markers are gone. The surface has changed. What was once a carefully chosen location now offers no trace of what was placed there. This experience is not rare. Antarctic research programs plan for loss. Budgets account for equipment that will never be recovered. Designs assume finite lifespans that may end early. Scientists accept this as part of working in a dynamic environment. What makes certain regions stand out is the consistency of loss. When multiple deployments in the same area meet similar fates, patterns emerge, instruments disappear faster, failure rates are higher, recovery efforts prove unproductive. Over time, these regions earn a reputation. This reputation does not mean that nothing can be learned there. On the contrary, the very processes that swallow equipment are often scientifically interesting. They indicate strong ice dynamics, high accumulation, or complex stress fields. But studying those processes directly becomes difficult when the tools required cannot survive long enough to collect meaningful data. Remote sensing offers some relief, but it has limits. Satellites can track surface changes and movement, but they cannot replace all in situ measurements. Certain data, such as detailed temperature profiles, chemical composition, or mechanical properties, require contact. When contact consistently leads to loss, scientists reconsider their approach. There is also an emotional dimension to this. Researchers invest significant effort in designing, building, and deploying instruments. Losing them is not just a financial setback. It represents lost opportunity, unanswered questions, and sometimes years of preparation that end quietly. Over time, this experience shapes attitudes toward risk. This is why avoidance develops gradually. It is not dictated from above. No one draws a line on a map and declares an area off limits. Instead, experience accumulates, stories are shared, data is compared, decisions become more conservative. In some regions, scientists deploy sacrificial instruments, low-cost sensors placed with the expectation that they will not be recovered. These experiments are designed to gather short-term data or to test conditions. They provide insight into how quickly and in what ways equipment is lost. This information feeds back into planning and design. Even so, there are limits. When loss becomes too frequent or unpredictable, even sacrificial deployments lose value. The data collected is too sparse, too brief, or too noisy to justify continued effort. At that point, regions transition from challenging to impractical. The swallowing of equipment is also not always physical. Data can be lost without visible damage. Sensors may remain intact but produce corrupted readings due to shifting conditions. Calibration drifts beyond correction. Communication links degrade. Storage systems fail. From the outside, the instrument still exists. Functionally, it is gone. These invisible losses are particularly frustrating. They can go unnoticed for long periods, wasting time and resources. In regions where this happens repeatedly, trust in instrumentation erodes. Scientists become cautious about deploying sensitive systems. There is an important distinction here. Antarctica does not destroy equipment out of hostility. It does so through indifference. The environment does not adapt to technology. Technology must adapt to the environment. When it cannot, loss follows naturally. This indifference is clearest in regions where multiple destabilizing factors overlap. High accumulation combined with fast ice flow, crevasse fields intersecting shear zones, variable basal conditions beneath complex surface topography. In these places, the ice behaves in ways that are difficult to anticipate even with good models. Maps do not show this complexity clearly. A region may look no different from its surroundings, but experience reveals otherwise. Teams learn to recognize warning signs, subtle surface textures, patterns of past loss. These cues inform future decisions. As a result, certain areas are approached only indirectly. Data is gathered from the edges. Models are refined using information from more stable regions. Scientists accept that some questions cannot be answered directly yet. This acceptance is not permanent. Boundaries shift as technology improves. Instruments become more robust. new methods emerge. What swallows equipment today may become accessible tomorrow, but until then, restraint remains part of responsible practice. The regions that swallow equipment without a trace serve as reminders, not of danger in a dramatic sense, but of the limits of control. They show that Antarctica is not a passive field site. It is an active participant in every experiment, shaping outcomes regardless of intention. As we move forward, these losses connect to another challenge. In some places, it is not just ice dynamics that complicate work, but weather patterns that behave in ways models struggle to predict. Areas where the atmosphere itself becomes an unreliable partner, adding another layer of uncertainty to an already complex environment. Weather is always a factor in polar science, but in Antarctica there are regions where it becomes something else entirely. Not just difficult, not just extreme, but persistently unreliable in ways that strain even the best forecasting systems. These are places where predictions hold only briefly, where patterns refuse to settle, and where the atmosphere behaves less like a system that can be modelled and more like a moving boundary condition that must be negotiated moment by moment. Antarctic weather is shaped by forces that operate at scales both vast and intimate. Global circulation patterns, ocean currents, and seasonal sunlight interact with local topography, ice surface texture, and temperature gradients that can change over very short distances. In many parts of the continent, these interactions are reasonably well understood. Forecasts are not perfect, but they are usable. In other regions, however, the atmosphere resists this kind of clarity. One reason is the lack of data. Weather prediction depends on observations, and Antarctica has very few permanent stations relative to its size. Those that do exist are clustered near the coast or along established logistical routes. Vast interior regions remain sparsely instrumented. Without regular ground-based measurements of pressure, temperature, humidity and wind, models must rely heavily on satellite data and extrapolation. Satellite data is invaluable, but it has limits. Clouds, blowing snow and temperature inversions can obscure readings. Surface conditions can interfere with infrared measurements. In some regions, the atmosphere behaves in ways that satellites struggle to interpret correctly. This creates gaps and uncertainties that propagate through forecasts. These uncertainties are not evenly distributed. Certain areas consistently produce less reliable predictions. Wind patterns there are influenced by subtle variations in surface slope and ice flow that are not captured well in large-scale models. Katabatic winds, cold dense air flowing downhill under gravity, can accelerate suddenly, change direction, or interact with other air masses in unexpected ways. In some regions, these winds are persistent and relatively predictable. In others, they are intermittent and erratic. A calm period can give way to violent gusts with little warning. Visibility can drop from clear to zero in minutes as blowing snow fills the air. Temperatures can plunge rapidly as air masses shift. For scientists in the field, this unpredictability is not an abstract concern. It affects every aspect of planning. Travel schedules, instrument deployment, aircraft operations, even simple tasks like moving between sites become contingent on conditions that may change faster than forecasts can track. Aircraft are particularly vulnerable to weather uncertainty. Many Antarctic operations depend on ski-equipped planes that require specific surface conditions to land safely. Snow hardness, wind speed, visibility, and temperature all matter. In regions where weather is difficult to predict, landing windows are narrow and unreliable. A missed window can delay operations for days or weeks. This has cascading effects. Fuel must be conserved. Supplies may run low. Personnel may be stranded longer than planned. In extreme cases, missions are aborted not because of immediate danger, but because uncertainty makes continuation irresponsible. Weather also affects ground travel. Oversnow vehicles depend on visibility and surface stability. whiteout conditions erase depth perception, making it impossible to judge terrain. Subtle slopes disappear, crevasses become invisible, even experienced guides can lose orientation. In regions with frequent whiteouts or rapidly changing conditions, the risk of disorientation increases. Navigation systems help, but they are not infallible. GPS signals can degrade. Compasses behave unpredictably near the magnetic poles. Redundancy mitigates risk, but does not eliminate it. There are also thermal effects to consider. Temperature gradients near the surface can create strong inversions, trapping cold air and altering wind behaviour. These inversions can persist for long periods, then break suddenly, releasing energy in the form of strong winds. Predicting when this will happen is difficult without dense observational networks. Storm systems behave differently in Antarctica than at lower latitudes. They can stall, trapped by the continent's geometry. They can intensify unexpectedly as they interact with cold air masses. Some storms dissipate quickly, others linger, reshaping surface conditions long after they pass. In regions where storms frequently stall or intensify, planning becomes speculative. A forecast that suggests moderate conditions may prove misleading. Scientists learn to read subtle cues, changes in cloud texture, shifts in wind sound, pressure trends. Even so, surprises are common. The unpredictability is compounded by seasonal extremes. During the Antarctic winter, darkness persists, limiting visual cues and satellite coverage. Temperatures are lower, weather systems behave differently. Forecast skill declines. Many regions are effectively inaccessible during this period. Even during the summer, when most fieldwork occurs, weather windows can be brief. A few days of suitable conditions may be followed by a week of storms. In some regions, these windows are so unreliable that scheduling fieldwork becomes impractical. This is one reason certain areas are studied primarily through long-term automated systems, if at all. But as discussed earlier, instruments themselves may struggle to survive in these environments. When weather unpredictability combines with equipment vulnerability, the result is a zone of persistent difficulty. Weather also affects interpretation of data. Measurements taken under changing atmospheric conditions can be difficult to compare. Wind-driven snow redistribution alters surface elevation readings. Temperature fluctuations affect sensor performance. Without stable conditions, distinguishing signal from noise becomes harder. In regions where weather variability is especially high, data quality suffers. Scientists may collect information, but confidence in its interpretation is lower. Over time, this reduces the value of direct measurements, reinforcing reliance on broader models and indirect observation. There is also the human factor. Living and working in an environment where weather cannot be trusted increases cognitive load. Constant vigilance is required. Plans must be flexible. Fatigue accumulates. Decision-making becomes more conservative. This does not mean scientists are unwilling to face bad weather. Antarctic researchers are trained for extreme conditions, but unpredictability is different from severity. Extreme cold that remains stable can be managed. Weather that changes rapidly and without clear warning is harder to accommodate. As a result, some regions acquire a reputation not for being the coldest or the windiest, but for being unreliable. Teams learn that forecasts there are often wrong, that conditions shift unexpectedly, that operations are frequently delayed or cut short. Over time, these lessons shape planning. Avoidance, in this context, is not fear-driven. It is efficiency-driven. When weather repeatedly undermines operations, resources are redirected. Scientists choose regions where effort is more likely to yield sustained data. This does not mean unpredictable regions are unimportant. On the contrary, their behaviour may hold key insights into atmospheric dynamics, climate feedbacks, and ice-atmosphere interactions. But studying them requires methods that can tolerate uncertainty. Remote sensing, long-term climate reanalysis, and modelling become primary tools. direct fieldwork is limited to reconnaissance or carefully timed missions. The atmosphere itself becomes part of the system being studied, rather than a backdrop. Antarctica's defiant weather reminds scientists that prediction has limits. Models improve, data accumulates, but there remain places where the atmosphere operates at the edge of predictability, influenced by local factors that are not yet fully resolved. These regions are not hidden. They are known, monitored, discussed. But they are approached with caution, because weather there does not behave as a cooperative variable. It intrudes, disrupts, and reshapes plans with little regard for intention. As we move on, this atmospheric unpredictability intersects with another challenge, one that is more personal and immediate. The effect of these conditions on the human body itself, and why even the most experienced researchers must accept limits, imposed not just by environment and equipment, but by physiology. Antarctica tests technology, logistics, and planning, but it tests the human body in quieter and more persistent ways. Not through dramatic moments of collapse or obvious danger, but through gradual erosion of physical and mental capacity. The body does not fail all at once. It adapts, compensates, and continues functioning, often long past the point where conditions have begun to undermine judgment, coordination, and resilience. This slow mismatch between human biology and Antarctic reality is one of the least visible yet most decisive reasons scientists avoid certain regions. The human body evolved for environments with moderate temperatures, predictable day-night cycles, and abundant sensory cues. Antarctica offers none of these. Cold is not just intense, it is sustained. Light is not just dim or bright, it is absent for months, or present without interruption. Sound is minimal. Visual contrast is low. The environment strips away many of the signals the body relies on to regulate itself. Cold is the most obvious challenge, but it is also the most misunderstood. People often imagine cold as something that can be solved with better clothing. In Antarctica, insulation helps, but it does not neutralize the problem. Prolonged exposure to extreme cold changes how the body allocates energy. Blood flow is redirected to protect vital organs. Extremities receive less warmth. Fine motor control deteriorates. Fingers become clumsy. Reaction times slow. This has practical consequences. Simple tasks take longer. Adjusting equipment, tying knots, handling tools all become more error-prone. Gloves reduce dexterity, but removing them risks frost injury within minutes. The body is constantly negotiating trade-offs between precision and protection. Cold also affects metabolism. The body burns more energy to maintain core temperature. Caloric needs increase, but appetite may not keep pace. Dehydration becomes a risk because cold suppresses thirst. Breathing dry, cold air increases fluid loss. Over time, even well-fed, well-hydrated individuals can drift into subtle deficits that affect endurance and cognition. Sleep is another battleground. Circadian rhythms depend on light cues, temperature variation, and routine. Antarctica disrupts all three. During the summer, continuous daylight makes it difficult to signal the body that it is time to rest. During the winter, prolonged darkness has the opposite effect, encouraging lethargy and low mood. Sleep deprivation in Antarctica is rarely dramatic. People do not stay awake for days at a time. Instead, sleep becomes fragmented, less restorative, shorter than planned. Over weeks this accumulates. Decision-making becomes less sharp. Emotional regulation weakens. Minor frustrations feel heavier. These changes are subtle, but in environments where safety depends on judgment, they matter. Altitude compounds these effects. Much of Antarctica sits at high elevation, particularly the interior plateau. Even though the ice surface may not look mountainous, the elevation can exceed that of many alpine regions. The air is thinner, oxygen availability is reduced. The body adapts, but adaptation takes time. In the interim, fatigue increases. Physical exertion feels harder. recovery takes longer. Headaches, nausea, and sleep disturbances are common during acclimatization. For scientists moving between elevations or arriving quickly by aircraft, this adjustment period overlaps with demanding work schedules. Cold and altitude together place strain on the cardiovascular system. The heart works harder to deliver oxygen. Blood pressure changes. For most healthy individuals, this is manageable, but it reduces margins. Pre-existing conditions that are trivial at sea level can become significant. The immune system also responds differently in Antarctica. Stress, cold, altered sleep and isolation all affect immune function. Minor infections can linger. Wounds heal more slowly. The body's usual defences are compromised, not catastrophically, but enough to matter over time. Medical support in Antarctica is limited. Even at major stations, facilities are designed for stabilisation, not comprehensive treatment. In the field, support is minimal. Evacuation may be delayed or impossible depending on weather and location. This reality influences decisions about who goes where and for how long. Psychological effects are less visible but equally important. Humans are social creatures, attuned to faces, voices, and movement. Antarctica offers long periods of monotony. The landscape changes little. Colours are muted, sounds are repetitive. This sensory deprivation affects mood and cognition. Isolation amplifies this effect. Field teams are small. Contact with the outside world is limited and delayed. Conversations become repetitive. Minor interpersonal tensions can grow. The environment does not offer distraction or relief. Some individuals thrive under these conditions. Others struggle quietly. Screening and training help, but they are not perfect predictors. Even experienced polar workers report periods of low mood, irritability, and mental fog. These experiences are normalized within the community, but they still influence performance. Risk perception changes as well. In unfamiliar environments, people are often more cautious. Over time, familiarity can breed complacency. In Antarctica, this shift is dangerous. Conditions may look the same day after day, but subtle changes can have serious consequences. Maintaining vigilance requires mental energy that is already in short supply. The body's stress response becomes chronically activated. Cold, isolation, and constant low-level risk keep stress hormones elevated. This affects sleep, mood, and immune function. Over long deployments, burnout becomes a concern. Nutrition plays a role here too. Antarctic diets are designed to be calorie-dense and shelf-stable. Fresh food is limited, especially in winter or in the field. Micronutrient balance can suffer. Vitamin D deficiency is common due to lack of sunlight. Supplements help, but they are not a perfect substitute for natural exposure. Hydration is another challenge. Melting snow requires energy and time. Water intake may drop unintentionally. Dehydration exacerbates fatigue and cognitive impairment. In cold environments, these effects can be mistaken for general tiredness, allowing them to persist longer than they should. All of this shapes how long people can safely work in certain regions. Some areas demand constant physical exertion. Others require long periods of exposure without shelter. In regions where environmental stresses stack up, the human body becomes the limiting factor, not technology or curiosity. This is not about weakness. It is about design. The human body did not evolve for sustained operation in Antarctica. It can adapt to a point, but adaptation has costs. Beyond certain thresholds, performance declines in predictable ways. Scientists are acutely aware of this. Fieldwork plans include strict limits on work hours, exposure time, and task complexity. Safety protocols exist not because people are careless, but because fatigue and cold alter behaviour in ways that are hard to detect internally. In regions where these stresses are especially intense, these protocols become difficult to maintain. Travel distances are long, shelter is limited, weather windows are unpredictable, the body's margin for error shrinks. This is one reason why some areas are avoided even when they are scientifically interesting. Not because the science is impossible, but because sustaining human presence there would push physiology too close to its limits for too long. There is also the cumulative effect of repeated exposure. Many Antarctic scientists return year after year. They know their own limits. They recognise early signs of strain. They adjust expectations accordingly. Regions that consistently demand more than they can safely give become less attractive over time. Technology can mitigate some of these challenges. Better clothing, improved shelters, more efficient heating, but it cannot eliminate the fundamental mismatch. At some point, the environment wins by attrition rather than force. The human body's relationship with Antarctica is not adversarial, it is conditional. With careful planning, support, and restraint, people can work there safely and effectively. Without those safeguards, the cost rises quietly and steadily. This is why avoidance is often framed not as fear, but as responsibility. Scientists understand that knowledge gained at the expense of health, safety, or long-term capacity is not sustainable. The goal is not to endure at all costs, but to understand within limits. As we move forward, these physiological limits intersect with another constraint. Even when the body can endure and the weather cooperates, the tools we rely on to see beneath the ice impose their own boundaries. And it is those boundaries, technological and conceptual, that shape where science can go next. From far above Antarctica, satellites offer a sense of mastery. They circle endlessly, tracing the continent with instruments that measure temperature, elevation, gravity, motion, and light. They deliver images that feel comprehensive, objective, and complete. It is tempting to believe that nothing escapes their view, that the age of blind spots has ended. But this belief does not survive long inside Antarctic science. Satellites see a great deal, but there are still places and processes that remain stubbornly out of reach. The limitation is not one of ambition or sophistication. Modern satellites are among the most complex machines humans have ever built. They can detect changes in ice thickness measured in centimetres, track movement across thousands of kilometres, and peer through cloud cover that once rendered entire regions invisible. And yet, Antarctica consistently reveals the edges of what orbital observation can do. One reason is depth. Satellites observe surfaces and near surfaces. They infer what lies below through indirect signals, radar reflections, gravitational anomalies, and thermal patterns. These methods are powerful, but they are not the same as direct access. When ice reaches several kilometers in thickness, signals weaken, scatter, or lose resolution. The deeper the target, the more interpretation replaces certainty. Radar can penetrate ice, but not uniformly. Its effectiveness depends on ice composition, layering, temperature, and impurity content. In regions where internal layers are complex or distorted, radar signals reflect unpredictably. Instead of clear boundaries, scientists receive noisy data that can be interpreted in multiple ways. Models fill in the gaps, but models depend on assumptions that may not hold locally. Gravitational measurements offer another window. Satellites can detect tiny variations in Earth's gravitational field caused by differences in mass distribution. From this, scientists infer bedrock topography and ice thickness. But gravity data is inherently coarse. It smooths over small-scale features. Sharp ridges, narrow valleys, and localized structures can be lost in the averaging process. What emerges is an outline, not a detailed map. Surface measurements also have limits. Satellite altimeters track changes in ice elevation over time, but interpreting those changes requires context. A drop in surface height might indicate melting, compaction, or redistribution of snow. Without ground-based validation, distinguishing among these possibilities is difficult. In some regions, the same signal can mean very different things. Atmospheric interference further complicates observation. Antarctica's atmosphere behaves differently than at lower latitudes. Temperature inversions, low humidity, and blowing snow affect how signals propagate. Infrared sensors struggle when temperature contrasts are low. Optical instruments are hampered by persistent cloud cover and seasonal darkness. Synthetic aperture radar helps, but it too has constraints. Seasonality introduces additional blind spots. During the long polar night, optical imaging is impossible. Some sensors rely on sunlight, others on thermal contrast. When the surface and atmosphere reach similar temperatures, contrast disappears, features blend together, changes slow, or become invisible to certain instruments. There is also the issue of resolution versus coverage. Satellites that provide high-resolution images typically cover smaller areas, or revisit locations less frequently. Those that offer frequent coverage sacrifice detail. Scientists must choose between seeing a little very clearly or seeing a lot more vaguely. No single system provides both at once. This trade-off matters in dynamic regions. Ice movement, weather events, and surface changes can happen quickly. A satellite might pass overhead just before or after a significant event, missing it entirely. Ground-based instruments can capture continuous data. Satellites capture snapshots. Orbit geometry adds another constraint. Polar orbits provide good coverage near the poles, but not all satellites follow ideal paths. Some regions are revisited frequently, others less so. Communication windows vary. Data latency can delay analysis. These factors shape what is noticed and what is missed. Subsurface processes are especially difficult to observe from space. Basal melting, subglacial water flow, and internal deformation leave subtle surface signatures, if any at all. Scientists infer these processes by combining multiple datasets, but inference carries uncertainty. In regions where surface expression is minimal, satellites offer limited insight. Even ice shelves, which float and are relatively thin compared to the interior ice sheet, present challenges. Changes beneath the surface, where ocean water interacts with ice, are largely invisible from above. Satellites can detect thinning, but not the precise mechanisms driving it. Oceanographic data is needed, and that requires instruments placed in difficult environments. Satellites also struggle with context. They measure physical parameters, but they do not capture the full story of how those parameters interact. A velocity change might be detected, but understanding why it occurred requires knowledge of basal conditions, stress history, and recent weather. Satellites provide pieces, not narratives. This is why satellite data is almost always combined with other sources. Ground-based measurements, airborne surveys, historical records, and numerical models all contribute. Satellites are central but not sufficient. There are also technical limits imposed by design life and cost. Satellites are expensive to build and launch. Instruments age, sensors degrade, calibration drifts, replacements take years, gaps appear in long-term datasets. In regions where change is slow but cumulative, these gaps matter. Some of the most challenging Antarctic regions coincide with these limitations. Areas with complex internal structure, high accumulation, dynamic flow, and unpredictable weather push satellite systems to their limits. Data from these places is noisier, less certain, harder to interpret. This does not mean satellites are failing. It means they are revealing the complexity of what they observe. The more detailed the data becomes, the more it exposes variation that cannot be resolved from a single vantage point. Scientists are careful about how they describe satellite-derived knowledge. They speak in probabilities, confidence intervals, and model ensembles. They acknowledge uncertainty. This caution is not weakness. It reflects an understanding that seeing is not the same as knowing. The public often imagines satellites as all-seeing eyes. Antarctic scientists know them as powerful but partial observers. They are invaluable for monitoring large-scale trends, detecting change, and guiding research priorities. But they do not eliminate the need for judgment, interpretation, and sometimes restraint. In some regions, the limits of satellite vision reinforce decisions to avoid direct exploration. When indirect data is already uncertain and direct access would be risky, scientists choose to refine models rather than push further. They wait for better tools. They accept incomplete knowledge. This acceptance is not resignation. It is part of working responsibly in an environment that does not yield easily to observation. Antarctica teaches that perspective matters. Seeing from above offers clarity and distance, but it also flattens complexity. Some details only emerge slowly, through accumulation of evidence rather than direct sight. As we continue, this theme deepens. Beneath the ice lie structures and processes that challenge not just satellites, but imagination itself. And it is there, below the reach of orbit and beyond the comfort of surface work, that Antarctica's most consequential uncertainties persist. Within Antarctic research, there is a phrase that rarely appears in headlines and almost never in popular descriptions, yet it carries significant weight in planning rooms and field briefings. Scientifically impractical. It does not mean impossible. It does not mean uninteresting. It does not even mean dangerous in the dramatic sense. It means that, given current tools, knowledge and constraints, the effort required to study a place directly exceeds the value of what would likely be learned. These zones are not officially designated. There are no signs, no borders, no formal prohibitions. Instead, they emerge gradually through experience, discussion, and comparison. A proposal is written, logistics are evaluated, risks are assessed, alternatives are considered, and quietly, without controversy, the conclusion is reached that this is not the right place to work, at least not now. Scientific impracticality is rarely caused by a single factor. It is the accumulation of many small disadvantages that align in the same location. Distance from support, unstable ice, poor weather predictability, high instrument failure rates, limited satellite resolution. Each on its own might be manageable. Together they create an environment where progress slows to a crawl. One common feature of these zones is logistical inefficiency. Reaching them requires long traverses or multiple flights with narrow weather windows. Fuel consumption is high. Support infrastructure is minimal or non-existent. Establishing even a temporary camp may require days of preparation. Once there, movement is constrained and contingency options are limited. In such settings, the ratio of time spent maintaining presence to time spent collecting data becomes unfavourable. Scientists may find themselves dedicating most of their effort to staying operational rather than to science itself. Equipment must be checked constantly, shelters maintained, routes reassessed. The work becomes dominated by survival logistics rather than observation or experimentation. Another characteristic is poor data return. Instruments deployed in these zones often produce incomplete, noisy, or short-lived data sets. Environmental conditions interfere with measurements. Ice movement distorts setups. Weather interrupts schedules. Even when data is collected, interpreting it can be difficult due to the complexity of local conditions. When this happens repeatedly, confidence declines. Scientists rely on reproducibility. If results cannot be replicated or validated, their scientific value diminishes. In regions where conditions make reproducibility unlikely, continued investment becomes harder to justify. There is also the issue of opportunity cost. Resources devoted to one project are resources not available for another. Antarctic research operates within finite budgets and limited seasonal windows. Choosing to work in a scientifically impractical zone means not working elsewhere. Perhaps in regions where data could be collected more reliably, or where questions are more urgent. This does not imply that impractical zones are unimportant. In fact, they are often important precisely because they are difficult. They may contain key dynamics related to ice stability, climate sensitivity, or geological history. But importance alone does not guarantee feasibility. Scientific practice involves prioritization. Questions are ranked not just by curiosity, but by tractability. This ranking changes over time as technology improves and understanding deepens. What is impractical today may become feasible tomorrow. But until that shift occurs, restraint is part of responsible decision-making. Ethics also play a role. Deploying people into environments where risk is high and benefit uncertain raises questions. Scientists are keenly aware that their work depends on trust, both within their teams and with the organizations that support them. Avoiding unnecessary exposure is not seen as caution, but as professionalism. Environmental impact is another consideration. Some zones are particularly sensitive, ice surfaces that record climate history in fine detail, subglacial environments isolated for immense spans of time. Disturbing these systems for marginal gains runs counter to the principles guiding Antarctic research. As a result, some regions are left alone not because they are unknown, but because they are known enough to warrant patience. Scientists monitor them indirectly, waiting for methods that minimize disturbance and maximize clarity. The designation of scientific impracticality is also dynamic. It is revisited regularly. New instruments are tested. New models reduce uncertainty. Improved logistics open possibilities. When conditions change, zones may be re-evaluated. This fluidity is important. It prevents stagnation. It ensures that avoidance does not become dogma. But it also acknowledges that progress is uneven. Not all frontiers advance at the same pace. Communication within the scientific community reinforces this process. Researchers share experiences informally as well as formally. Reports of failed deployments, unexpected conditions, and logistical bottlenecks circulate. These narratives shape collective understanding. Over time, consensus emerges about which areas are worth pursuing directly and which are better studied from afar. This consensus is rarely unanimous, but it is influential. Early career scientists learn from veterans, funding agencies listen to field reports, planning committees weigh recommendations. The label of scientific impracticality becomes a shorthand for accumulated wisdom. It is worth noting that this label does not imply permanence. Antarctica has a long memory, but science has a longer one. Techniques that once seemed unrealistic become standard. Questions that once lacked context become central. Zones marked impractical are not abandoned, they are deferred. Deferral can last years or decades. During that time, indirect observation continues. Satellites track change, models are refined, theoretical frameworks evolve. When the moment is right, attention returns. In the meantime, these zones occupy a quiet space in Antarctic science. They are acknowledged, respected, and watched. They influence models and risk assessments. They remind researchers that not all knowledge comes from direct contact. This approach contrasts with popular ideas of exploration as conquest or completion. In Antarctica, exploration often means knowing when not to go further, when to wait, when to accept partial understanding as preferable to overreach. Scientifically impractical zones embody this philosophy. They are not blank spaces on a map, but carefully considered absences. They represent choices shaped by experience, not by fear or indifference. As we move deeper into the continent's hidden complexity, these choices become even more consequential. Beneath the ice lie features that challenge not just logistics and instruments, but fundamental assumptions about what can be accessed at all. And it is there, under layers of moving ice and ancient pressure, that Antarctica holds some of its most persistent uncertainties. What lies beneath Antarctica is not hidden in the dramatic sense. There is no single secret waiting to be uncovered by one decisive expedition. Instead, there is depth, layered upon depth, compressed by time and pressure, until the very idea of beneath becomes difficult to define. Miles of ice do not simply cover the continent, they reshape it, interact with it, and in many places sever it from direct human reach in ways that fundamentally limit what science can do on site. Beneath the Antarctic ice sheet lies a landscape that has not been touched by sunlight for millions of years. Mountains, valleys, basins and plateaus exist there much as they would anywhere else on Earth, but they exist under conditions so extreme that ordinary geological intuition breaks down. Pressure is immense. Temperatures hover near freezing not because the environment is mild, but because pressure lowers the melting point of ice. Heat seeps upward from Earth's interior, just enough to keep parts of this hidden world active. This bedrock landscape is not smooth. It is rugged and deeply sculpted, shaped by tectonic forces long before Antarctica froze over. Ancient river systems once carved channels through it. Fault lines fractured it. Volcanic activity reshaped it. When ice advanced, it filled these features, preserving their outlines while obscuring their details. Scientists know this landscape exists because of indirect evidence. Radar pulses bounce off the ice bed interface. Seismic waves change speed as they pass through different materials. Gravity measurements reveal variations in mass. From these signals, researchers reconstruct a picture, but it is always incomplete. Resolution decreases with depth. Small features blur. Sharp boundaries soften into gradients. What makes this subglacial world especially challenging is that it's not static. The ice above it moves, and that movement interacts with the terrain below. Where bedrock slopes downward inland, ice becomes unstable, more likely to retreat if conditions change. Where ridges rise, ice may anchor itself, resisting flow. These interactions are central to understanding future sea level rise, yet they occur entirely out of sight. Water complicates this picture further. At the base of the ice sheet, pressure and geothermal heat melt ice into liquid water. This water does not always flow freely. It pools in subglacial lakes, some as large as small seas, others no bigger than a city block. It travels through channels that open and close as ice shifts above them. It lubricates motion, alters stress, and redistributes heat. These subglacial water systems are among the most intriguing and inaccessible environments on Earth. Some have likely been isolated for hundreds of thousands of years. They may host microbial life adapted to darkness, pressure, and scarcity. Studying them could reveal insights into the limits of life and the history of Earth's climate, but accessing them directly is extraordinarily difficult. Drilling through kilometers of ice requires immense energy, precision, and time. The borehole must remain open long enough to deploy instruments. Contamination must be avoided. Equipment must survive pressure changes and extreme cold. Even when these challenges are met, the act of drilling alters the environment being studied. For this reason, only a handful of subglacial environments have been accessed directly, and each attempt has been the result of years of planning and international collaboration. Many others remain untouched, not because they are unknown, but because the cost of access is too high relative to what can be learned safely. Volcanic features add another layer of complexity. Antarctica hosts numerous volcanoes, many buried beneath ice. Some are dormant, others may still be active. Heat from these systems can thin ice from below, influence water flow, and destabilize surrounding regions. Identifying and monitoring these features relies heavily on indirect methods. In some areas, seismic data suggests active magma beneath the ice. In others, geothermal heat flow is higher than expected. These signals are important, but they are difficult to interpret without direct sampling. Once again, depth imposes limits. The pressure beneath miles of ice also affects rock behavior. Bedrock may deform differently under these conditions. Chemical reactions proceed along unfamiliar pathways. Minerals interact with water in ways rarely observed at the surface. These processes matter for long-term landscape evolution, but observing them directly remains beyond current reach. Even the ice itself changes with depth. Near the surface, ice is brittle. Deeper down, it becomes ductile, flowing rather than fracturing. Crystals realign, layers fold. Information stored in ice cores becomes harder to interpret as deformation increases. Below certain depths, records are stretched, compressed, or mixed beyond easy reconstruction. This means that even when scientists drill deep ice cores, there are limits to what those cores can tell us. The oldest ice is often the most distorted. Extracting clear climate signals from it requires careful modelling and cautious interpretation. All of this contributes to why certain regions are avoided, not because they lack scientific value, but because their most important features lie beneath depths that current technology can barely access. Working at the surface provides limited insight. Going deeper introduces risk, cost, and uncertainty. There is also the issue of irreversibility. Once disturbed, subglacial environments cannot be returned to their original state. Introducing heat, pressure changes, or contaminants alters conditions permanently. Scientists weigh this heavily when considering direct exploration. As a result, much of what lies beneath Antarctica remains inferred rather than observed. Models grow more sophisticated, data accumulates slowly, understanding improves incrementally. This is not a failure of science, it is an acknowledgement of scale. Miles of ice represent not just a physical barrier, but a boundary between observation and inference. They force researchers to work patiently, to accept uncertainty, and to resist the urge to rush toward answers. The hidden world beneath Antarctica is not waiting passively. It continues to interact with the ice above, shaping the continent's response to a changing climate. Scientists watch for surface signals that hint at deeper changes. They listen for seismic whispers. They refine their models. For now, much of this world remains beyond direct reach. And that reality shapes which questions can be asked safely, which methods are appropriate, and which regions remain observed from afar rather than entered. As we move forward, this deep uncertainty blends with something more human. Around these hidden spaces, stories begin to form, rumours circulate, speculation fills gaps left by limited access, and understanding where those stories come from helps clarify what Antarctica is and what it is not. When access is limited and certainty arrives slowly, stories rush in to fill the space. Antarctica has attracted rumours and myths for as long as people have known it existed, and the regions scientists avoid have become especially fertile ground for speculation. From hidden civilizations to secret research bases, from ancient technologies to unexplained signals, the narratives vary widely, but they share a common origin. They arise where information is partial, indirect, and difficult to verify. These stories are rarely born from malice. More often, they grow from misunderstanding. When people hear that areas are unexplored, avoided, or inaccessible, imagination steps in. Silence becomes secrecy. Distance becomes intention. The absence of clear answers invites dramatic explanations, because they feel more satisfying than uncertainty. Within the scientific community, these myths are familiar. Researchers encounter them regularly, sometimes as genuine questions, sometimes as confident assertions. They understand why they persist. Antarctica does not offer the transparency people expect from modern science. Data is slow to collect. Fieldwork is rare and costly. Many results are technical, probabilistic, and cautious in tone. This creates a gap between public expectation and scientific reality. One of the most common misconceptions is that avoidance implies concealment. If scientists do not go somewhere, the assumption follows that they are choosing not to reveal what is there. In reality, avoidance usually reflects limitation, not intent. The reasons are logistical, environmental, or ethical, not conspiratorial. Another persistent myth involves the idea of forbidden zones, areas allegedly closed off by international agreement to hide discoveries. The Antarctic Treaty does restrict certain activities, particularly military use and resource extraction, but it does not designate secret regions for concealment. Restrictions exist to preserve the environment and promote cooperation, not to withhold knowledge. The notion of hidden structures beneath the ice appears frequently in speculative narratives. Ancient cities, lost continents, advanced civilizations frozen in time. These ideas often draw loosely from real scientific concepts, such as subglacial lakes or buried mountain ranges, then extend them far beyond evidence. The existence of complex geology beneath the ice is real. The leap to human-made structures is not supported by any credible data. Seismic surveys, radar mapping, and gravity measurements have revealed the shape of the bedrock with increasing clarity. Large anomalies are detected and investigated. Nothing resembling artificial construction has ever appeared in these data sets. Scientists would not overlook such findings, nor would they be able to hide them easily within an international research community that thrives on publication and peer review. Another class of myth centers on unexplained signals, strange radio emissions, anomalous readings, unidentified seismic events. In many cases, these stories begin with genuine scientific observations that are later resolved. Antarctica's environment produces unusual data. Ice cracks generate seismic signals. Atmospheric conditions affect radio propagation. Cosmic particles interact with the ice in detectable ways. Early interpretations may be uncertain, and preliminary findings sometimes reach the public before full analysis is complete. When updates arrive quietly, or explanations are technical, the initial mystery lingers in popular imagination. The gap between discovery and explanation becomes a breeding ground for speculation. There are also myths rooted in historical expeditions. Early explorers encountered extreme conditions with limited technology. Their journals describe optical illusions, strange sounds, and disorienting experiences. These accounts are fascinating, but they reflect human perception under stress rather than hidden phenomena. Long periods of darkness, fatigue, and isolation alter how the brain interprets sensory input. Modern researchers understand these effects well. They're part of the reason psychological screening and support are integral to Antarctic programs. The environment does not just challenge the body, it challenges perception itself. The quiet truth behind these myths is less dramatic but more revealing. Antarctica is difficult to study because it operates at the intersection of extreme scale, slow processes, and limited access. It resists simple narratives. Scientific explanations are often conditional, provisional, and technical. They do not lend themselves to dramatic storytelling. This does not mean scientists dismiss public curiosity. On the contrary, they recognize it as a sign of engagement. But they also know that certainty in Antarctica comes slowly. Models improve incrementally. Data accumulates over decades. Confidence grows cautiously. The scientific method thrives on transparency, but transparency does not always mean immediacy. Results must be validated. Data must be checked. Interpretations must be tested against alternatives. In an environment where measurements are sparse and conditions are variable, this process takes time. Rumours often ignore this timeline. They compress uncertainty into intention. If something is not explained quickly, it must be hidden. This logic misunderstands how science works, particularly in extreme environments. Another source of myth is the scale of Antarctica itself. Its sheer size invites exaggeration. It is easy to imagine that something extraordinary could be hidden there simply because there is so much space. And while it is true that much remains to be understood, extraordinary claims still require evidence. Size alone does not create secrecy. Scientists are also constrained by language. When they speak carefully about uncertainty, their caution can be misinterpreted as evasion. Phrases like "not yet understood" or "requires further study" can sound unsatisfying to audiences accustomed to definitive answers. This dissatisfaction can fuel alternative explanations. The reality is that many Antarctic questions do not have clean answers. Ice dynamics involve feedbacks and thresholds. Subglacial systems evolve. Atmospheric interactions shift. Understanding emerges from patterns, not single revelations. There is also the influence of media and entertainment. Antarctica has become a backdrop for fiction that blurs the line between speculation and fact. These stories are compelling, but they shape expectations. When reality does not match the narrative, disappointment can morph into suspicion. Within the research community, there is little appetite for secrecy. Antarctic science is inherently collaborative. Data is shared across nations. Findings are published openly. Projects involve teams from multiple institutions. Concealment would be difficult to sustain, and contrary to the culture of the field, the truth is quieter. Scientists avoid certain areas because they have learned, through experience and evidence, that presence does not always equal understanding. They recognize that some environments impose costs that outweigh benefits. They choose indirect observation not to hide but to respect limits. This restraint is often misunderstood as hesitation or fear. In reality, it reflects confidence in method. Knowing when not to act is part of expertise. The myths persist because they are simpler than the truth. They offer clear villains, hidden motives, and dramatic revelations. The truth offers conditional statements, error bars, and ongoing work. It requires patience. As technology advances and access improves, some myths fade, others adapt, new gaps appear. The cycle continues. Antarctica remains a place where imagination and reality intersect, not because it conceals secrets, but because it refuses to simplify itself for easy understanding. The quiet truth behind the rumours is that the most interesting questions about Antarctica are not being hidden. They are being worked on slowly, carefully, and often indirectly. Progress happens in increments, not leaps. And as we move forward, this distinction becomes even more important, because beyond rumour and speculation lies a deeper reason scientists hold back. Not because they are afraid of what they might find, but because they understand what it would cost to push further before the time is right. Curiosity is often portrayed as an unstoppable force, something that naturally pushes forward regardless of cost. In practice, scientific curiosity is more measured than that. It is guided, constrained, and sometimes deliberately slowed by an understanding of risk. In Antarctica, this restraint becomes especially visible. There are questions scientists are genuinely interested in answering, questions that could deepen understanding of climate, geology, biology, and planetary systems, and yet those questions remain unanswered, not because they are unimportant, but because answering them directly would demand risks that are not justified yet. Risk in Antarctica is rarely dramatic. It does not usually involve a single catastrophic scenario. Instead, it accumulates through layers of uncertainty, environmental unpredictability, equipment vulnerability, human physiological limits, logistical fragility. Each layer increases the chance that something small could cascade into something serious. When scientists talk about whether a question is worth the risk, they are weighing all of these layers together. One of the most important considerations is irreversibility. Some actions cannot be undone. Drilling into a subglacial lake, for example, permanently alters that environment. Even with the strictest contamination controls, the act of access introduces heat, pressure changes, and foreign materials. If something goes wrong, if equipment fails or protocols break down, the consequences are lasting. In these cases, scientists ask not just what might be learned, but what might be lost. Another factor is marginal gain. Not all questions yield equal returns for equal effort. In some regions, indirect data already provides a reasonably clear picture. Models are constrained. Trends are understood within acceptable bounds. Direct access might refine details, but not enough to justify the added risk. When this is the case, patience becomes a rational choice. Risk is also temporal. What is too dangerous today may become manageable in the future. Technology advances, methods improve, experience accumulates. By waiting, scientists increase the likelihood that when a question is finally addressed directly, it will be done with greater precision and lower cost. This perspective contrasts with popular narratives that frame delay as failure or avoidance. In Antarctic science, delay is often strategic. It reflects confidence that understanding improves over time, even without immediate intervention. Human safety is central to these decisions. Antarctic researchers accept risk as part of their work, but they do not accept unnecessary risk. There is a clear distinction between calculated exposure and avoidable danger. When a question requires placing people in environments where rescue is unlikely, conditions are unstable, and the scientific payoff is uncertain, restraint is seen as the responsible choice. This responsibility extends beyond individual researchers. Field teams rely on support staff, pilots, engineers, and logistics personnel. A risky mission puts many people at risk, not just those asking the scientific question. Ethical considerations weigh heavily here. No data set is worth a life. There is also the issue of cumulative exposure. Antarctic programs run year after year. The same individuals or institutions often return to the field repeatedly. Pushing too hard in one season can have long-term consequences for capacity and morale. Fatigue, burnout, and injury reduce future effectiveness. Sustainable science requires pacing. Some questions are postponed because answering them would monopolize resources. Large-scale drilling projects, deep field camps, or complex traverses require extensive support. Funding, equipment, and personnel devoted to one high-risk question are unavailable for other projects that may yield broader benefits. Scientific communities are not immune to competition, but Antarctic research tends to emphasize collaboration. Decisions about risk are often made collectively. Proposals are reviewed by committees with diverse expertise. Concerns are raised. Alternatives are suggested. The process is slow by design. This deliberation sometimes frustrates outsiders who expect bold exploration. But within the community, it is understood as a safeguard. It ensures that enthusiasm does not override judgment. Another reason some questions are deferred is interpretive uncertainty. Even if access were possible, the data collected might be ambiguous. In highly complex environments, measurements can be difficult to contextualize. Without sufficient background information, results may be hard to interpret correctly. Waiting allows models and indirect observations to mature, providing a framework into which future data can fit more meaningfully. There is also the possibility of unintended consequences. Intervening in one part of a system can affect others in unforeseen ways. Antarctica is tightly coupled to global systems. Disturbing ice, water, or ecosystems has implications beyond the immediate site. Scientists are cautious about triggering changes they cannot predict or reverse. This caution is informed by history. In other environments, well-intentioned interventions have led to long-term damage. Antarctic research, shaped by international agreement, places a high value on preservation. The continent is treated not as a resource to be exploited, but as a shared scientific reserve. The phrase, "not worth the risk yet," carries an implicit optimism. It suggests that the question remains valid, that it will be addressed when conditions improve. It is not a dismissal. It is a postponement grounded in respect for limits. This respect extends to uncertainty itself. Scientists are comfortable with not knowing everything at once. They recognize that some gaps will persist longer than others. They accept that incomplete understanding is preferable to overconfident error. In this sense, Antarctic science differs from exploratory traditions that prioritize firsts and breakthroughs. Here, success is often defined by what did not go wrong, by data collected without incident, by seasons completed safely, by incremental progress sustained over decades. There is also humility in these decisions. Antarctica repeatedly reminds researchers that nature does not yield to ambition alone. It sets its own terms. Ignoring those terms leads not to discovery, but to loss. Some of the most important Antarctic questions concern long-term change, ice sheet stability, sea level rise, climate feedbacks. These are not questions answered in a single expedition. They require continuity, consistency, and trust in data. Risky ventures that jeopardize these qualities undermine the very goals they seek to advance. As a result, scientists often choose the slower path. They monitor, they model, they wait. When they act, they do so deliberately. This approach can be difficult to communicate. It lacks drama. It does not produce immediate revelations, but it reflects a mature understanding of both the environment and the scientific process. The questions that are not worth the risk yet are not forgotten. They remain part of the collective agenda, revisited as conditions change. Each advance in technology, each improvement in understanding, shifts the balance slightly. Until then, restraint is not an obstacle to knowledge. It is a condition of it. And as we move onward, this restraint shapes how Antarctica is perceived more broadly. Not as a frontier to be conquered, but as a boundary that defines where human inquiry must slow, adapt, and sometimes step back. Antarctica is often spoken about as a place to reach, the last continent, the far edge of the map, a destination defined by distance rather than by purpose. But within the scientific community, Antarctica is understood very differently. It is not a goal to be arrived at and completed. It is a boundary, one that marks the limits of certain kinds of human activity and forces a reconsideration of how knowledge is pursued. A destination implies arrival and closure. You get there, you explore, you leave with something definitive. Antarctica does not offer that structure. Every arrival is provisional. Every departure leaves more unanswered than resolved. The continent does not invite completion. It enforces continuation without resolution. This boundary is not only physical, though its physicality is undeniable. Ice thickness, cold, isolation, and scale impose limits that cannot be negotiated away. But the deeper boundary is conceptual. Antarctica exposes the point at which traditional models of exploration stop being effective. The assumption that proximity equals understanding breaks down here. In most environments, progress follows a familiar pattern. Observation leads to access. Access leads to control. Control leads to explanation. Antarctica interrupts this sequence. Observation does not reliably lead to access. Access does not guarantee control. Control, when attempted prematurely, often leads to failure. This forces science to operate differently. Instead of pushing forward until resistance is met, researchers learn to read resistance itself as information. A region that cannot be safely accessed is not a blank, it is a signal. It tells scientists something about the system's scale, dynamics, and sensitivity. Seen this way, Antarctica functions as a kind of natural filter. It selects which methods are appropriate and which are not. It rewards patience, indirect reasoning, and long-term observation. It punishes haste, overconfidence, and simplification. This boundary reshapes ambition. Rather than asking, how do we get there? Scientists increasingly ask, what can we learn without going there? The focus shifts from conquest to inference, from presence to pattern recognition, from short-term discovery to long-term understanding. This is not a retreat from curiosity, it is an expansion of it. By accepting Antarctica as a boundary, researchers open new ways of thinking about evidence, uncertainty, and scale. They learn to integrate signals from disparate sources. They build models that respect complexity rather than override it. The boundary also enforces humility. In environments where human systems dominate, it is easy to forget that not everything is accessible or controllable. Antarctica restores that perspective. It reminds scientists that nature does not owe clarity on demand. This humility is embedded in Antarctic governance. International agreements emphasize cooperation, preservation, and restraint. No single nation controls the continent. No one claims ownership. Scientific activity is framed as stewardship rather than exploitation. This reinforces the idea that Antarctica is not a prize, but a responsibility. Treating Antarctica as a boundary also affects how success is measured. Success is not defined by how far one travels or how much territory is covered. It is defined by continuity of data, safety of personnel, and integrity of systems. A season that yields modest results without incident is often valued more than a risky push that ends in loss. This perspective can be frustrating for those who expect dramatic breakthroughs, but it reflects a deeper understanding of the environment. Antarctica does not respond to intensity, it responds to consistency. The boundary is temporal as well as spatial. Many Antarctic processes unfold over timescales far longer than human projects. Ice flow, climate cycles, geological change. These processes cannot be rushed. They require observation across generations. Antarctica teaches science to think in longer arcs. This long view reshapes priorities. Instead of chasing singular answers, researchers focus on trends. Instead of definitive conclusions, they build frameworks that can adapt as new data arrives. The boundary becomes a guide, not a wall. It also changes how absence is interpreted. Areas without direct measurements are not failures. They are acknowledged gaps, documented and monitored indirectly. Their absence from fieldwork plans is often deliberate, informed by the understanding that forcing access would not improve insight. In this sense, Antarctica acts as a mirror. It reflects the strengths and weaknesses of scientific methods. It shows where tools are robust and where they are brittle. It reveals assumptions that hold elsewhere but fail under extreme conditions. This reflection has implications beyond polar science. Techniques developed to work around Antarctic boundaries influence research in other extreme environments. Deep oceans, planetary surfaces, astrobiology. Antarctica becomes a testing ground not for dominance, but for adaptability. Seeing Antarctica as a boundary also reframes public perception. It shifts the narrative from mystery and secrecy to limitation and responsibility. The unanswered questions are not hidden behind barriers. They are positioned at the edge of what current methods can responsibly reach. This framing does not diminish the continent's importance, it enhances it. Antarctica becomes a place where science learns about itself, about how knowledge is constructed, about when to act and when to wait. The boundary is not fixed. It moves slowly as technology improves and understanding deepens. What lies beyond it today may fall within reach tomorrow, but the existence of the boundary itself remains constant. There will always be aspects of Antarctica that resist direct engagement. Accepting this does not weaken science. It strengthens it. It encourages rigour over bravado, reflection over impulse. It aligns inquiry with the scale of the system being studied. As the story continues, this idea settles into something quieter. Antarctica does not challenge humanity to conquer it. It challenges humanity to recognise where effort should end and attention should begin. And in that recognition, something essential about the nature of knowledge comes into focus. Antarctica does not rush. It does not respond to attention, urgency, or expectation. Long after plans are postponed, instruments are withdrawn, and questions are set aside, the ice continues doing exactly what it has always done. It accumulates, it flows, it presses downward and outward with a patience that makes human timelines feel brief and provisional. This quality, more than any other, defines the continent. It waits, not because it has something to reveal on cue, but because its processes unfold at scales that do not bend toward immediacy. When scientists step back from certain regions, the ice does not change its behaviour. It does not become quieter or more dramatic. It does not signal disappointment or relief. It simply continues. Snow falls, redistributed by wind. Layers compress. Basal ice warms under pressure. Water moves unseen beneath kilometres of frozen mass. The surface may appear unchanged year to year, but beneath that appearance, motion persists. This patience is not passive, it is active continuity. The ice is always recording, always responding to forces that act upon it. Atmospheric changes leave signatures in snowfall. Ocean temperatures influence ice shelves from below. Geological heat shapes basal conditions. Everything that happens around Antarctica becomes part of the system, stored and translated slowly into physical change. From a human perspective, this can feel frustrating. Research operates on grant cycles, field seasons, and publication timelines. Questions are framed with the hope of answers within years, not centuries. Antarctica does not align with these rhythms. It resists compression into convenient intervals. This mismatch is one reason restraint becomes a defining feature of Antarctic science. Scientists learn that some answers will not arrive quickly, and forcing them can degrade understanding rather than improve it. Patience becomes a methodological choice, not just a personality trait. The ice's patience also reframes loss. Instruments swallowed by snow or carried away by flow are not failures in the Antarctic context. They are markers of engagement with a system that does not pause for observation. The continent absorbs effort and continues, indifferent to whether data was retrieved or not. This indifference can be unsettling, but it is also clarifying. It removes any illusion of control. It places human activity in proportion to the environment it seeks to understand. Antarctica does not need to be protected from science. Science needs to be shaped to fit Antarctica. The waiting ice also preserves. Within its layers are records of atmospheres that no longer exist, chemical traces of volcanic eruptions, particles from distant deserts, signals of climate shifts that unfolded long before human observation. These records persist because the ice is slow to change. It locks information in place, not perfectly but well enough to be read with care. Preservation, however, is not stasis. Over time, layers deform. Records stretch and compress. Older information becomes harder to interpret. The ice waits, but it does not guarantee clarity forever. There is a balance between patience and attention. Wait too long, and some details may be lost. Act too quickly, and context may be destroyed. This balance underlies many decisions to postpone direct exploration. Scientists are not only weighing risk to people and equipment, they are weighing risk to information itself. Disturbing an environment prematurely can compromise the very signals they hope to study. The ice's patience also influences how uncertainty is tolerated. In many fields, uncertainty is treated as a problem to be eliminated. In Antarctic science, it is treated as a condition to be managed. Models are built with ranges rather than single outcomes. Predictions are expressed probabilistically. Confidence grows gradually. This approach is sometimes misread as hesitation. In reality, it reflects alignment with the system's pace. Antarctica teaches that certainty earned slowly is more durable than certainty claimed quickly. Waiting also allows for convergence. As years pass, multiple datasets accumulate. Satellite records lengthen, models are refined, independent observations begin to align. Patterns emerge not from single measurements, but from consistency across time and method. The ice does not rush these patterns. It allows them to reveal themselves when enough evidence exists. There is also an ethical dimension to this waiting. Antarctica is not owned, it is shared. Decisions made today affect what can be studied tomorrow. Exercising restraint preserves options for future researchers with better tools and broader perspectives. The ice waits, and in doing so, it invites science to think beyond individual careers or projects. This long view is difficult in a world accustomed to acceleration, yet it is precisely what Antarctica requires. The continent rewards those who can hold questions open without demanding immediate closure. Even climate change, which introduces urgency, unfolds unevenly in Antarctica. Some regions respond rapidly, others change slowly. Understanding these differences requires patience. Rushing to conclusions risks oversimplifying a system that is deeply heterogeneous. The waiting ice also reframes hope. Hope in Antarctic science is not tied to dramatic breakthroughs, it is tied to continuity, to the idea that careful observation, sustained over time, will yield insight. That understanding will deepen not through conquest, but through accumulation. This is why some regions remain untouched, not because they are irrelevant, but because they will still be there when the moment is right. The ice does not forget. It does not erase its history quickly. It holds it, compressed and layered, waiting for methods that can read it without undue cost. From this perspective, Antarctica is not withholding knowledge. It is setting terms. It asks science to meet it with patience, humility, and adaptability. Those who accept these terms find progress, even if it arrives slowly. The image of waiting also applies to the human relationship with the continent. Expeditions come and go. Stations are built and dismantled. Programs evolve. The ice remains. It absorbs these cycles and continues. This continuity can be grounding. It places human effort within a larger context. It reminds researchers that they are participants in a long process, not protagonists in a single story. In the end, Antarctica does not demand that it be fully known. It allows itself to be partially understood, gradually through careful attention. The ice waits, not because it must, but because it can. And in that waiting, it shapes the kind of science that approaches it. A science that values restraint as much as discovery, that measures progress in decades rather than days, that understands boundaries not as failures, but as guides. So the unanswered questions remain. They are not abandoned, they are held in suspension, monitored from afar, revisited as tools improve. The ice continues its slow work, storing information, releasing signals, reshaping itself. Nothing is paused, nothing is final. The waiting is active, ongoing, and deeply informative for those willing to see it that way. And as this quiet journey reaches its natural resting point, the continent remains where it has always been, at the edge of maps and methods, patient and indifferent, holding its history beneath layers of moving ice, ready when science is prepared to listen at its pace.